Dr. Stewart for the audience. So he joined Professor Ben Adams, who is a well-known lecture community person, research group in Bingham University as an undergraduate student. So Professor Adams' group moved to Yale University and Dr. Wright earned his PhD from Yale in 1992. So his thesis research focused on automating EBSD. So whatever you're seeing, the current EBS system, there is a lot of work which he has done 25 years back. After Yale, Stewart joined Los Alamos National Lab as a postdoc, working under Dr. Tony Rollett. Stewart left Los Alamos in 1995 to join PSL, which is now EDAX and Ambitech, as an EBSD startup company. So PSL was bought by EDAX, and Stewart now is a senior scientist at EDAX, focused on EBSD development. So a lot of this OEM software which you use is basically coming from Dr. Stewart's development work. So I'd like to thank you for coming here and having this nice workshop. So the origin of this is that we have recently purchased or acquired a high resolution or fast EBSD camera known as Velocity. So that's got installed a few weeks back. So I thought it was a good occasion to have a workshop like this so that we can know the latest trends in this technology. So the program is like this. We have in the first half, I have made you the agenda for the workshop. So 9:30 to 11 we have a introductory lecture followed by a short break. And 11:30 to 1 again lecture by him. So 1 to 2 is a lunch break. And 2 to 5 we will have laboratory demonstrations. So since I want to make sure that everybody gets a demonstration, what we have done is we are going to demonstrate the lab experiment through live streaming in a room, not here. We will take you to another conference hall in another building. So you all can sit there, and with this camera setup, which we are anyway live recording this entire event. So the demonstration will be done by the next team. So you can all watch it live. So that everybody gets the demonstration. Okay. And then tomorrow we will lectures here. So we will assemble here at 9:30 and then entire day. Second half we will have interactive session and so on, which I gave you in the program. So this is the overall plan for this program. Okay. So now I will hand over to Dr. Stewart to start with it. Thank you.
It's good to be with you here. It's actually my second trip to Chennai, and maybe third. I forget. I travel around quite a bit. And I live in a desert, and so it's nice to see green, and it's a beautiful campus that you have here in Chennai. So thank you. I'm glad to be here. So this morning, this first lecture is going to be very introductory to both EBSD and somewhat to EDS and some of the other techniques that we support at EDAX. I hope it's, some of it will be a review for some of you, but I hope there will be enough meat here to keep your attention. So I want to start with this slide and ask the question, what is microstructure? And we think of microstructure, we think of things like the shape of the grains that we see, second phases, inclusions, pores, cracks, things like that. And you can see all these things in various micrographs, either optical or in the SEM. But there are some things that you can't obviously see in a picture. And so can we capture some of that? And one of those is orientation, and another is chemistry. You see indications of this in the pictures, but you can't measure them quantitatively from a single image. So can we capture some of this information? Other things include the deformation state. Are these things that we can capture in a quantitative way? So let's start out. This should be a review slide for all of you. What are the signals that come from the SEM, or in this case a TEM? You have your incident beam. From that, you get a lot of different signals. You get elastically scattered electrons, inelastically scattered electrons. You get X-rays in various forms, and different electrons, as they interact with the sample, produce different signals. Now if we switch to the SEM, I start with the TEM because that's basically where microscopy started, was in TEMs. But if you think about an SEM, we get a little bit different signal, and that's because we basically block out the signals that are coming out of the sample, and they're now absorbed into the sample. But we still see some things. We still see backscattered electrons, which are the ones I'm going to focus on. Secondary electrons tell us something about the surface of the sample. You have X-rays, you have Auger electrons, and visible light. Now, what do some of these images look like? Backscattered electrons, generally we think of those as providing Z contrast, elemental contrast in the microscope. Secondary electrons generally give us an idea of the surface, what the topography or topology looks like. Visible light, most commonly we think of cathode luminescence, which tells us something about the chemistry and state of the material. And there's Auger electrons, they also give us composition very much right at the surface. And there's characteristic X-rays, which we will talk about too. So why do we get X-rays? Well, the electron comes in, and what it does is it knocks a electron from the atomic structure, from the atom. And so you can get an emitted electron with atom, an electron emitted from the atom, which is the Auger electrons. From the SEM, you get the incident beam reaction. But because you have a movement here of one electron will move down to another shell, from the L shell to the K shell in this example, you get a characteristic X-ray. And so this information we can capture in the SEM. So EDS, here's a typical configuration, EDS detector, capturing those signals. And so you can create EDS maps if you control the electron beam and track the EDS signal, the energy dispersive with an energy dispersive spectrometer. Then you get an idea of the spectrum at every point, and you can map out the composition of your material. Just as an example, here's some EDS maps from a sample. Here's what the secondary electron sample looks like, showing the topography of the material. And then we have all these different signals. And you can see then where different chemical species are in your material. If we go back to this picture, the TEM, you'll see here elastically and inelastically scattered electrons. So what happens to these when we go to SEM? Well, if we tilt the sample like this, now we give these, we're kind of in a mixed mode almost. Because what we're doing is we're giving these electrons now a chance to escape, and we can detect them. Now I want you to think about, and this is typical configuration for EBSD. And we have an incident electron beam. But what we usually do is think of this as the source of the electrons. We think of an embedded source in the material. So you can kind of ignore the idea of this beam coming in. And that's because what we have is we have this interaction volume as the incident beam interacts with the crystal. And you have electrons going out in all directions. So infinite, you can think of it almost as an infinite number of electrons in an infinite number of directions. And that's an important concept when it comes to EBSD. And that's because of Bragg's law. As those electrons are coming back out of the sample in directions, they all have different angles. And as they interact with the atomic planes, those that satisfy Bragg's law give us a signal. They give us a coherent diffraction. So if you think about it this way, we have the electrons, an electron coming in from some direction. It interacts with the plane, and it produces these cones of diffraction, sometimes called causal cones. And you end up with a pattern. If you put a phosphor screen in here, you end up with a pattern that looks like this. When electrons hit the phosphor screen, they luminesce the screen, and you basically are converting electrons to light. And from that, you can detect this with film or with a camera, and you can get a pattern. So these planes in the pattern are reflect these curved lines. And you'll see you don't see the curvature, but it is there. I'll show you an example later. But these planes, these bands here, correlate to planes in the crystal structure, in the crystal lattice. As an example here, this is a very nice pattern from silicon. And these are the different, some of these are the reflectors in our material, and I've just assigned them colors, just randomly. But if you look really, really close, for example, this band here, you can see there's a slight curvature of that blue line. This one is from nickel, sorry. And if you look here in the silicon, there's a very nice pattern. You can actually see multiple orders. So you have 111 planes, 222, 333. So you can see multiple orders of material. And the solid angle we're capturing here is about 70 degrees approximately, at least typically. And if you look really close, you can see some curvature. This band's a little fatter here and a little narrower near the center. And that's the hyperbolic nature of diffraction. And these kind of patterns, we call them EBSD patterns, electron backscatter diffraction. But it's Kikuchi, but diffraction, but we usually think of Kikuchi in the TEM. And there can be some confusion about what to call these patterns. The community has settled on EBSD. It may not be actually the right name, but that's what we've settled on. Some people have called them BKD, backscatter Kikuchi diffraction patterns in the past. And with the advent of TKD, that's resurrected this argument of what should we call them. But I'll come back to TKD later. But for now, I'll continue to refer to them as EBSD patterns. So some things to look for in the patterns. Remember, I mentioned, that's the right one, Bragg's Law. No, that's not the right one. I'm going the wrong direction, sorry. Here we go. We have Bragg's Law, which is lambda equals 2d sine theta. D is the spacing of the atoms in the atomic plane. Theta is the angle, the electron, the incoming angle of the electron relative to the plane. Lambda is the wavelength of the radiation. And lambda, you calculate the wavelength with this lovely equation here. And the important part here is the electron voltage. So this is the kV that we can see on our microscope. And if you do that, then notice the voltage. This is the voltage. This pattern's at 7 kV. This one's at 50 kV. And so you can see it's actually exactly the same pattern. This band here corresponds to that band there. This one is here. But the bands are much wider here. And that just has to do with this equation here and where these voltages come into play. So at high kV, we get very sharp lines, and they're much narrower, and you can see many more reflections in the material. So we typically operate around 20 kV, but in a typical SEM arrangement, you can operate down to, say, 10 kV. There are a few microscopes, SEMs, that can go to higher voltages, such as 30 and up to 40, and I guess up to 50. This is a pattern given to me by a colleague. I'm not really sure where it came from, but typically you can't get to 50 kV in a microscope, a typical SEM. So why do certain bands appear and not others? And it has to do with the atomic planes, as I mentioned. So we know that the intensity of the bands is a function of the structure factor. And the structure factor is calculated like this according to kinematic theory. You have a atomic scattering factor here. These are UK or HKL are the position is the indices of a diffraction or a crystallographic plane. The UKV, usually I use XYZ, but UKV is the positions of the atoms within the unit cell. So from that you can calculate a structure factor. This is just an example for salt. And if you do that, then you can calculate the strength of these bands. The important factor here is this one, the atomic scattering factor. It's a function of this big equation. The key thing I want you to note here is Z, the atomic density. So if I do a diffraction pattern for aluminum, it looks like this. The EBSD pattern for tantalum looks like this. This is at the exact same conditions. You can see in the tantalum, which has a high Z, you see a lot more bands, there's a lot more intensity, and you're able to get it's a little easier to get diffraction patterns from heavy materials than it is from the materials higher up on the periodic table. So let's get back to EBSD. So the key here is we have a stationary electron beam. As it interacts with the sample, it produces diffraction, and we can capture that with, like I said, a phosphor screen here. Behind the phosphor screen are lenses and a camera to detect the patterns. And it's the geometrical arrangement of the bands that we're interested in, because that tells us the orientation of the crystal lattice in the diffraction volume. So as an example, I put my beam on my sample here on this grain, I get this pattern, and I get that pattern because the crystal is oriented this way. If I move the beam, I get a different pattern because it's a different orientation. And I can just move the beam around the sample and you get nice patterns. And you hope you get nice patterns. Some samples are a little tougher, and some of you have probably experienced that sometimes all you see is gray and no bands at all. But we'll come back to why that can be. So what's the hardware for EBSD? Once again, it's mounted here below the EDS detector. You can see the camera's inside this box, and there's a tube that goes in. The camera's actually inside the tube, so we can get it close to the phosphor where the illumination's happening, and we can get everything as tight as we can in the material. Inside that, there's actually inside this box, there's actually a bellows slide for vacuum integrity, and like I said, a phosphor screen. So now we've added this into the mix, the EBSD detector. What we have is the electron beam. We move it to a point. We capture a pattern. From that, we use something called the Huff transform to find the bands in the pattern. Once we find the bands, we look at the angles from them, and we're able then to determine the crystallographic orientation, and we record it to the disk in the terms of 3 Euler angles in this example. And I'll go through these steps, but we call this whole process indexing. This is indexing an EBSD pattern. Now, at a point, we can also record the EDS data from the EDS detector. We can record any data from any other detectors, such as the secondary electron detector or a backscatter detector, for example. And so we record all that data at each point. And that's quite helpful, because then we can start to do some really nice things. The most interesting, I think, is the orientation map. We color the grains according to their crystallographic orientation. In this case, the blue ones have 111 axes coming out normal to the screen, and that's the 111 here. The red ones are 001s. You'll see here, there's a nice 001. Where's a really nice flat? There's one right here. So you have the face of the cube parallel to the sample surface. 110, you have an edge of the cube parallel to the sample surface. So this tells us the orientation of the crystal at each point. Because we know the orientation, we can calculate the difference in orientation from one grain to another. And in this case, I've colored the grain boundaries according to the amount of misorientation or disorientation. And I'll come back to all these concepts in more detail. So what can we use EBSD for? There's really, at this point, 2 main application areas, or there's some others, but these are the 2, and the others are kind of embodied in here. One is phase identification, and the other is orientation imaging microscopy, or OIM, or OIM. And let's start with phase ID. The idea behind phase identification is that you put your beam on a sample or a feature of interest in the SEM field of view. From that, then, you capture an EDS spectrum to learn the chemical composition of your sample. In this case, it's primarily made up of titanium, oxygen, or titanium, iron, and oxygen. You capture an EBSD pattern from the same point, go back to this EDS spectrum, and go to some database. And there's a lot of databases out there, and I'll talk about those later. But this is a chemical database, and from that we know the phases. So from that database, we take the various parameters, such as the lattice parameters and other factors, and we use that information to try and index this pattern. And if you do that, you can see then that this top one seems to be the best match, Fe2TiO4. And so we can use all this information to get a positive identification of the phase. Now this is nice and easy, not easy to do, but relatively straightforward idea, assuming your database has the phase of interest. If the phase of interest is not in your database, then this gets really hard. And there's a fair amount of research still going on in this arena, but I wouldn't say that it's become routine at all. It's very difficult and requires a lot of interpretation. Just to show you, you can do this. This is a rock. There's 7 different phases in it. We're able to positively identify all 7 of these phases using that approach. And there is some work going on in phase ID, but I would say that's 5–10% of users are doing that process. It's really not all that common. The primary use is this imaging idea. And so here's just one of the very first samples that I did. This is a tantalum rod cut from a forged plate, and we were interested in the variation in texture because when we compressed it, instead of getting this or a straight cone or a straight cylinder, we got this hourglass shape where the ends strained faster than the center line of that, and that is due to a change in orientation. So the blue is material that's in a stiff orientation relative to the compression axes, and the red is in a soft orientation. So I want to just go through quite several applications here just to show you what EBSD can do. So really, I would say we did a little study in looking at all the journals and all the EBSD papers, and we found overwhelmingly that these kind of deformation ideas are the #1 use of EBSD. Probably around 60 to 70% of the papers out there are dealing with deformation and strain. So it's interesting because this is one of the very first things I did, and that's continued to be the use is in EBSD. This was more of an engineering example than it is material science, really, but it just shows what can be done. Another area is looking at growth and recrystallization. This is a deposition here. It's indium oxide films on an MgO substrate. And this is just one snapshot. There's a very long surface that was examined by Jeff Ferrer. And what you find here is that initially you'll notice there's quite a bit of blue, which is the 111 orientation parallel to the sample surface. And you'll notice this is red. So it's not it's definitely not a epitaxial growth or nucleation. It actually you get 111 nucleation. But as these grow, there are a few 111 types, these red, close to red, and they're the ones that grow. And the growth of these blue ones tends to get pinched off and replaced with those 111 grains. And if you look over the whole structure, you'll see it's really dominated by red at the surface and blue at the beginning. So it's an oriented growth mechanism. Here's another example. This is dendrite growth in silicon. And beautiful images from the microscope here, and you can see then some interesting growth of a twin relationship in this dendrite. There's actually 2 twins here, but this isn't high enough resolution to see both. So this just shows various growth and how they interact, and they compared those with AFM measurements. Very nice study that's getting pretty old now, but still good. Another area are phase transformations. And we can see these in EBSD. This is some in situ work I did with my colleagues. I don't know, it's been almost 20 years now, or 15 years, I guess. And so what you see here is the blue boundaries are the final beta boundaries, and these are the cyan ones are the final alpha boundaries, and we track that as we deform the material. And what's interesting here to me is that you can see here's the 111 plane in the beta phase. This is in cobalt, and the basal pole in the hexagonal phase, and they're right on top of each other. So you can see this phase transformation going as expected. This was mostly a test for us to make sure that we could do in situ work. Here's a nice study application out of Germany. from 2001. This is the study of oxide formation after exposing titanium to an electrochemical bath. So what he did was to correlate the crystallographic orientations with the activity, and they could measure this. Basically, what you see is the colors in this map are due to changes in layer properties and thickness, and they tell us something about the electrical chemical activity. And they used these little lines here as fiducials, and then took the EBSD data and put it in the bath, and they were able to see a clear correlation between the orientations and the activity. Another early application that I think was pretty remarkable work by Gino Palumbo is stress corrosion cracking. And so we used EBSD. Like I said, we can measure misorientations across grain boundaries. And in this study, they were looking at special misorientations, in particular twin boundaries. These are sigma 3 twins. The yellow ones or the blue ones are sigma 9 twins, which is a secondary recrystallization twin or FCC materials. And you even get a few of these third or ternary twins, which are sigma 27 boundaries. And if you have a lot of these, then you have when you put the battery grid into its bath, you are able to retain the integrity of the grid, but without any special boundaries, you can see it just falls apart. It's a really dramatic example of how EBSD can be used to solve real materials problems. Some stuff that's kind of fun and off the beaten path. EBSD has been used in archaeology. There's a nice, I should have brought the example, there's a nice study, I think out of IIT Mumbai or Bombay, on a Damascene sword from India. But this one's out of Copenhagen, Denmark, or at a museum in Copenhagen, Denmark. It's called the Gundestrup Cauldron, came out of the peat bog, and it's starting to fall apart as it's been exposed to air. And so they actually took a little piece of it, put it in the microscope to try to understand what's happening to it. And you can see it's starting to corrode primarily at the grain boundaries, although there is some transgranular corrosion as well. I don't know if this has helped them solve the problem. I don't, but it's kind of an interesting study. At least they know why it's happening. So I mentioned strain and deformation and good and bad patterns. So let's talk a little bit about that. So I'm going to talk about plastic strain here. And in general, plastic strain produces poorer patterns than unstrained materials. So this is a very nice example of zirconium, unstrained, strained. And so this manifests its way. The other way that strain manifests itself in the material is a slight change in orientation. As the material deforms, it slips, and you get very small rotations. And so the pattern difference here, you probably can't even see it by the naked eye, but if you look really close, this zone axis right here, and that one, it's a little farther away from the edge here. So there's a slight change in orientation across that grain. And we call these local misorientations, and they tell us something about the material. So strain manifests itself in terms of poorer patterns and also changes in orientations. So you can create maps based on these two ideas to see where the deformation is in your material. So this is what we call a pattern quality or image quality map. The dark regions here are because the patterns are poor. This shows the quality of the patterns. So the dark regions are poor patterns, which indicate strain. And the nice clear grains are recrystallized material, and they produce nice sharp patterns. We can also look at that if we look at local misorientation, which is subtle changes in color. And you'll notice in this grain here, you'll notice the change in color from almost blue all the way up to red, which is a pretty big change in orientation. You can see bands of different colors within these areas here. But if you look at a recrystallized grain like here, or here, or here, the color's constant. And that's because there's no change in orientation. There's no deformation. There's no dislocations in the material. As an example, this is, just to show you how this works, this is a series of OIM maps we took during in situ heating of a deformed copper sample. And this is the first slide. And you can see it's very muddled, lots of changes in color, so it's heavily deformed. Let's see if this works. It never does. Oh, there it is. I cannot see that on my screen. So you can see recrystallization starting to happen. You get these grains popping in that are all solid color, and the twins that are forming. It's jumping around a little bit because we couldn't quite get a line between each slide. But you can really see the deformation happening. And you can see there are some areas that did not recrystallize. Let's see some of these small areas here. And so we were looking at this study is to try to understand why some grains would start and recrystallizing more quickly. It's both a nucleation effect, but also a orientation effect. And some of those grains are either oriented in such a way that nuclei can't form, or there's not quite enough deformation to have the driving force for that recrystallization. We can also do 3D serial sectioning so that we can study these grain boundaries. So this is another application area, is the study of grain boundaries. And so this is an example from Stefan Zeffer at Max Planck Institute in Düsseldorf, Germany. And so they looked at these boundaries here in 3 dimensions so that they could get not only the misorientation but also the orientation of the grain boundary plane, and then they could start to study the grain boundaries in this way. And this is just an example of that I showed earlier. Now, to this point, I've only pretty much showed single-phase materials, but EBSD can be used to study materials of many different phases. This is a nice rock example. You can see there's, 7 different phases here. We can map the orientations of all those. We can figure out which phases we're working with. And in this case, we are using both EDS and EBSD together to get to this phase map, because some of these are easy to differentiate by EBSD, and some are easy to differentiate by EDS. And so we use both techniques to understand the phases in our material. Another material we've looked at is this Gibeon meteorite, which is kind of a famous meteorite that was discovered in 1836. It broke into many different fragments, and the material is very, very coarse-grained. So this is a coarse-grained structure. You can see this is 5 millimeters, and you can see these huge grains in this meteorite. And if you look really close, you can see some unevenness in the image quality map here. And there's really little blocks, and each of those is an individual scan using the beam, and then we move it with the stage to another position, scan again, do this process many, many times, stitch it all together to capture the microstructure at this level. So I can't remember how many individual scans here, maybe 1,000 individual scans here, and it all stitched together. So it's a really pretty example. Another one I always thought was fun is this one is, I don't know if we have any geologists here, but I thought I would throw a few in for fun. This is, these are called trilobites. There's some found in the mountains around where I live, so I've always been interested. But their eyes were made of calcium carbonate, or calcite, and so they're actually already a rock, in essence. So that part of the animal is not a fossil. It's actually the original eyes that we can see in these animals. And so it's, with this material is transparent in one direction, but not in the other directions. So we can look at EBSD of these eyes, and you can see they have a hexagonal structure, and you can see the light. This is the top surface of this, and then the animal's sensor, or eye, is essentially down here. And the light would come in, and they could see. And you'll see they bend over like this. And what they found is that if they bend over a lot, they think those are animals that lived in where there's a lot of light, so they could see animals around them to eat. Or escape from animals that want to eat them. And if they were straight up, then they were deep water trilobites, where their only light is above them. So they believe they learned a little bit about these animals from these eyes. I think it's still one of my favorite applications of EBSD. Here's another one about eggs. So this is a chicken egg. This is an ostrich egg. And it's really interesting. These long, very large grains here, elongated grains, actually exhibit some deformation in them, and so they're tougher. And if you've ever tried to break an ostrich egg, I haven't, but I understand it's quite difficult compared to a chicken egg, which we could all do quite easily. And they use that information to look at two types of dinosaurs, a big plant eater and a raptor. And it turns out the raptor's eggs are more like chicken eggs, and the big Titanosaurus's eggs are more like ostrich eggs. And so from that, they're able to postulate the temperature. I don't know how they do this, but they're able to figure out the temperature at which those eggs are laid. And it tells them something about the dinosaur. So next time you go to the dinosaur museum, you can look at the eggs and be a little more excited. Another interesting application in biology is what they did is attach gold nanoparticles to a protein and put that inside, embed that in a wet cell. So there's water inside here. There's a polymer film to keep it from leaking out, and a carbon film on top of that. And then they activate the crystal and watch how, or the protein, watch how it moves, and use the EBSD from the nanoparticle there, and they can track then how that protein behaves under various conditions. So applications that I never dreamed it would be used for, but are kind of emerging and are kind of exciting. So I want to give you, that's just an introduction to applications. We'll go into more detail over the next couple of days. But before we start that, I want to give you just a brief history of EBSD. The very first patterns really are Kikuchi patterns. This is the Kikuchi of Kikuchi patterns. And there really are diffraction patterns. So the next steps, there were some nice patterns out of Germany, wide-angle Kikuchi patterns. These are done these are all done in chambers, in vacuum chambers, not in microscopes at this point. It's before microscopes. But in 1973, Venables and Harland at University of Bristol in England put a camera or some film in an electron microscope, tilted the sample, and were able to actually get diffraction patterns in the SEM. So this is kind of where EBSD really starts. And David Dingley, who was also at the University of Bristol, then got involved and wrote a program for online analysis of EBSD patterns. And in this system, I actually got to use this system. In this system, you would go in and you'd have to be knowledgeable enough to recognize this is a 110 type zone axis, this is a 112, 001, and click on those points and it would be able to figure out the crystallographic orientation. And so David did some really nice work through the 80s with this and joined our group at Yale University. I was working with Professor Adams, a student of his. David Dingley joined our group for a while, and I was assigned the project of trying to automate the detection of these bands, or these patterns. So what we did is use some image processing techniques to try and find the bands, and then once again I look at the angles between these, and I'm able to index the pattern. And this is the very first, or one of the very first samples that we did. It was an aluminum sample, and we colored the grains according to some orientation scheme. And that was 1992, or actually it was in the fall of 91. So, like I said, the very first EBSD patterns, or diffraction patterns period, were in the 20s, and it kind of moved along, and then David Dingley came along, and there started to be a lot more interest. You can see a lot more papers during this period. And then once we automated it, things just took off. I've stopped keeping track. It's too hard now. Google Scholar can do it somewhat for me, but you know, these papers, EBSD's in the title. These papers, EBSD's in the abstract. These papers, it's buried somewhere in the paper. So the indexing, searching algorithms don't always find it. So it's harder and harder to track what's going on. And not everything's published anymore. Companies are doing eBSD work, steel companies, metals companies around the world are doing eBSD work and they're not publishing. So it's really grown. It's been great for me to be a part of this and be a part of this growth. So we founded TSL in 1994 in Utah. We called it Texture in the SCM. That's what TSL stands for. And we were the first group to try to commercialize this. In 1999, EDAX purchased TSL, and we became a part of that. This was our team at about that period, with a few visitors in here as well. We're located in Utah, which is in the western United States. This is the eBSD group. We also have headquarters. Our headquarters are near New York City, out here on the East Coast of the United States. We have real eBSD expertise in Tilburg in the Netherlands. René de Clou, who some of you may have met, he's been to India quite a bit. We also have some folks who are pretty good at eBSD in Wiesbaden. And then we have expertise, I need to update this slide, in Tokyo, actually in Shanghai is where our group is now in China. And then the Amitech EDAX offices here in India are in Bangalore. But we have other people around the country. So it's grown quite a bit since those early days. So to understand eBSD, I need to explain more about crystallography and diffraction. And I really hope this is a review for most of you, which is good and bad. It means it's boring if it's a review, but if it is a review, it means you already understand it and won't need much of it. So in order to interpret the diffraction patterns, we have to have some understanding of diffraction and crystallography. But we don't really need to know all the complexities. We've tried to put all that into the software so you don't have to deal with it. And with each generation of software, we put in more and more detail because basically you as users are demanding more and more detail to solve more and more sophisticated problems with eBSD than we imagined when we started. So in terms of crystallography, we need to know something about the unit cell. We need to know about planes and directions and symmetry, and that really comes back to all this. In terms of diffraction, Bragg's law is still the governing function of eBSD, and we need to understand that, and how point and space groups fall into that, and other factors that influence the patterns. So I'm going to go into some detail here. So the unit cell, we need to know ABC, the length of the vectors defining the unit cell, and then we need to know their direction as well, which are defined by the angles alpha, beta, and gamma. We need to know about crystal planes, directions, and axes. So there's 7 crystal systems. You can see the different symmetry operations that are part of that. And I'll come back to this idea as to these systems. So just to show you that we can get patterns from all of them, here's triclinic. This is kyanite, which is a triclinic mineral. Monoclinic, orthorhombic, and trigonal. You'll notice all my lower symmetry ones tend to be minerals, and that's just because that's what you deal with when you deal with minerals, is their lower symmetry materials. PZT is a good example of a tetragonal structure. Magnesium, this is a hexagonal structure. Titanium, another good example. And cubic, this one's from stainless steel. So we use the standard HKL Miller indices to define planes in the crystal. And hopefully that's just nothing new there. But you'll notice that, so these are planes, these are bands correspond to planes. Sometimes we call these reflectors, these planes that produce the bands, and sometimes we call these reflections, the appearance of the reflectors in the planes. And we use the 4-index notation for hexagonal crystals. So a note about planes. D-spacing is somewhat important in eBSD, although not critical. And just to show you an example, as we go to higher indices, the atoms are actually farther apart on the planes. And so they have, the lines of lowest indices have the greatest spacing and density of lattice points. So, this is a very simple, these are just 2-dimensional examples. The spacing is defined by this big equation, which takes into account the lattice parameters and the symmetry in a sense. So I bring up the D spacing because of this picture I showed earlier. And so you can see the different orders. And what you know immediately is this is going to be a low index plane, and this big fat one's going to be a high index plane. And there's some in here that are really big planes that, like, if you look really close, you can see the shadow at one edge here, another edge up here. That's probably a very high index, or a very very high index plane that's producing that reflection. Now, when planes come together, we call those zone axes where they intersect, and they correspond to poles in our material. And this all comes into play because of symmetry, and we generally worry about point group symmetry in EBSD, although really we worry about Laue group symmetry, and I'll come back to this idea. So point group symmetry defines the set of rotations, which is a point group, which when applied to the crystal lattice rotated into an orientation that can't be differentiated from the original orientation. So for example, if I take an 001 axis here, rotate it 90 degrees about that, this cube will be in an orientation I can't tell the difference. And you know, I show other examples here, but that should be, we should be able to see that in the diffraction patterns. And so this is a cubic one right here. This 111 is a threefold axis. And so you see here there's 120 degrees between those two, you know, 100, 120. And you can see there's a 121, 211, and 112. Here's an 001, which is a fourfold axis, and you can see that there. You have those 90 degree apart, and these two 90 degrees apart. And this is an 001 axis, so I have a 60 degree rotation. So you can see this in the patterns, but because of the 70 degree tilt and where the camera is located, it's not always obvious, and you kind of have to let the computer do this for you. So here's, for example, if my sample were tilted 90 degrees, my 001 would be nice and symmetric like you see here. But because we're tilted at 70 degrees, or somewhere near 70 degrees, you can see this is now distorted. And so the symmetry is not always obvious in the patterns. And this brings up an idea of pseudosymmetry. And in my mind, there's two types of pseudosymmetry. There are others, but two main types. One is a structure that mimics a symmetry, and I'll come to this idea of two stacked cubes. The other is something that's just slightly stretched, and tetragonal is a very good example. Probably many of you are familiar with martensite in steels, and martensite is actually a base-centered tetragonal structure, or BCT structure, but it's very close to BCC, the ferrite structure. And BCC is a nice cubic structure with cubic symmetry, but BCT is tetragonal. But it's only 1% tetragonal, or 2%, maybe up to 3%, depending upon the carbon content. And so it stretches the crystal lattice a little bit. So the stacked cube idea is this one. So this is kesterite, copper, iron, tin, sulfur. And I can't remember which is which. I think it's this is copper, and the red is copper, and the green is iron. And so this structure here is almost like two stacked cubes. And that's because under diffraction, the copper and the iron actually are pretty similar. And so indexing this material is really difficult. You get structures like this that are just completely nonsense. They're just random orientations. And that's because of this effect. So what I have here, you can see the cube in three different orientations. But if you look at the blue cube, it's actually in the same orientation in all three cases, even though the overall structure is in the three differentiable orientations. And if you look at the patterns, they're almost identical. And so you can see EBSD would have a hard time differentiating these three orientations. And we call this pseudosymmetry. And it's a problem that we see, one of the challenges of EBSD in certain materials. If you look really close, you can differentiate these, especially if you look at these two. If you look at this little band up here near the top, it's really close to the edge here and a little farther interior here. So there is some hope you could differentiate these, but usually the patterns, these are simulated patterns, and the patterns from this material are usually not very good. So it's really becomes impractical. Now the other one I mentioned was this stretched cube idea. And it may not be just cube, it could be other structures, but the cube's the easiest to understand. So this is PZT. It gets stretched. That's part of what creates the electric dipole, which gives it its piezoelectric properties. But it's only slightly tetragonal. I've exaggerated it here so you can see it. But if you look at the patterns from that structure, you can see they're almost identical, even for these two different orientations. If you look really close, you can see this band here, the overlay doesn't match the pattern quite as well as this one, and they're shifted from each other. So in this one, there is a little bit of hope of differentiating these, but typically that would be a difficult sample to do. And so we call this pseudosymmetry. Usually what happens is we end up indexing this as if it were just cubic, which is a shame because then we've lost some information. But we're working on different techniques to try to improve this. And this brings me to the idea of central symmetry. So in theory, EBSD breaks Friedle's rule, which governs X-ray diffraction. So in simple terms, it means in EBSD, we should be able to differentiate HKL from H minus K minus L in non-central symmetric crystals. But in standard indexing EBSD patterns, we only look at the positions of the bands in the patterns. We're only looking at where does this band appear in the pattern. So that's the geometry. We don't consider the intensities, and it's the intensities that differentiate these two. Let me show you an example. Just to show you, so here's the crystal, the Lowy groups. Here's the point groups. These are the central symmetric ones, which are the names of the Lowy groups, and these are the non-central symmetric ones. So here, for example, is quartz. There's two types of quartz, left-hand and right-hand quartz, and you can see the space groups are slightly different. And what you see here then is, if you look at these patterns, the positions of the bands, the intensity of the band all look exactly the same. But if we go into really fine detail, and these are, once again, simulated patterns, and I'll talk about simulated patterns later today. But you'll see here, look at the intensity difference between this little shape here and this little shape here. If you look here and here, they've switched places. There's a little kind of dot in the center there, and it's moved to the right, and here it's on the left. And so these are the subtle differences we have to be able to see to really separate non-central symmetric crystals from each other. So generally, in EBSD, we really assume all the materials we look at are central symmetric at this point, because if we do indexing, we really are just concerned with the angles between bands. So that, I hope, gives you an idea of some of the diffraction and crystallography that's involved. And some of it, like I said, we can see, some of it we can't. So the key to all this is good patterns. Whenever you see patterns like this, we use in all of our literature. Whenever you see papers published, everybody has beautiful patterns. But if you don't do your sample preparation correctly, your patterns start to look like, oh, yeah, these ceiling tiles. You can't see anything in them. And trust me, the very first ones I did by hand, I did in a lab at 2 o'clock in the morning because that was my microscope time. And the next day in my courses, I sat there and looked at these ceiling tiles all day long and said, oh, look, there's a 111. Look, there's... It's amazing that I survived those PhD years. And yeah, so this is the kind of pattern you might expect to see if you don't do the sample preparation right. So this is just a quick sequence. This is the material after grinding and polishing to 1200 micron on the silicon carbide papers. And then we did an alumina polish, followed by a 0.3 micron aluminum polish, followed by 0.05 microns colloidal silica on a vibratory polisher. And so if you look at the image quality, which is a description of how good these patterns are, you can see that this will have low image quality, this will have high image quality. The other thing that can affect that is if you have to coat your materials. If you do too thick of a coat, the image quality goes down very quickly. And so if you're working with non-conductive materials, ideally you would do it in an environmental SEM, but if you don't have access to that, then you probably need to coat them. And if you do that, we recommend using a very thin coating of carbon. That seems to give the best results. What we've also found is that if you take a sample, so if you have it in a polishing disc of some kind and you have your samples right in the middle, it really makes sense to coat everything around your sample quite heavily and then just coat very thinly over your sample. So what we'll do is we'll do a thin coating over the whole puck or disc, and then just paint by hand around the sample with silver paint. That seems to work well. Now, ideally you have samples that are polished, but just to show you, you can do rough samples. It's just that you get a gradient, which can make it difficult for the indexing routines to work, and I'll show why later. So this is just another sequence here. There's a lot of improvement when I go from the silicon carbide paper to alumina. Less improvement as I go along, but this is a really good example of nickel, so you really don't have to polish it as well as maybe some other things. But we typically do, go through all the basic polishing steps, including alumina, and then we usually finish with this colloidal silica on a vibratory polisher. Now there's other ways to do that, and I think I have a few slides on that. Now, even this pattern looks good, but we've picked the best pattern off the sample we could find. If you actually were to try to do a scan, you can see that there's still you see evidence of scratches in the material and some pores. And so it really makes sense to go to a better polish. And you can see I get really nice improvement once I get out here and do the colloidal silica step. Just another word or two. I'm showing mechanical polishing results. You can use electrochemical approaches, and they work great. The other thing that people are using is to use a fib, which is great if you have access to a fib, or a broad beam ion polisher. It's just that if you use the fib or broad beam ion polisher, you'll need to not be too aggressive. You need to work maybe at lower voltages and use a glancing angle, because that will improve your results quite a bit. Why does that happen? And that's because of deformation. So if you look here, this is greatly exaggerated. The interaction volume is much bigger than this, but just to show an example, if I have a dislocation in my material, I've disrupted the atomic lattice. And now I've got, instead of satisfying Bragg's law on a single plane, Bragg's law is actually kind of shifting as it moves around here. So I have electrons satisfying Bragg's law at several different angles or orientations, and so I end up with a smearing of the patterns. And that's one effect you can get. And you can see that after sample preparation. So this is an example. We did 1200 grit silicon carbide on I think it's a steel sample, and this one's only to 240. And then we cross-sectioned it and actually polished it up properly. And what you can see is this deformation layer. The colors are showing us deformation. I'll explain how later, but the brighter the color, the more deformation. You can see this is much thicker than on the 1200 grit. If I were to go then to even more polishing, this would disappear. And so our electron beam has to get through this. Our electron beam has to get through this and back out. And so if we have a deformed layer on the surface, it's very much going to affect our patterns, because EBSD is very much a surface-sensitive technique. And so it's important to prepare samples in such a way you can get rid of that. So if you need more details on sample preparation, I would check our website. There's some good information there, and a couple of webinars, I believe, on sample preparation in a lot more detail than we have time for during my visit. So I want to go into some of what I'm calling here operational foundations in terms of what it takes to index a sample. And the reason I do this is because as you're indexing, if you're having problems, it helps to understand the foundation of things like the Huff transform and the indexing algorithms, so you understand how to tweak the software and tune it to get the best results possible. Now, and hopefully you don't run into this. Hopefully the software just, in its default parameters, does the job for you. But if it doesn't, you might find these are the things you're going to have to play with. So one of the things is spatial resolution, and we need to talk about this. The electron beam comes in, and if our material has a lot of grains, or fine grains, then our interaction volume may contain several grains. And so each one of those would give a nice pattern by itself, but if our interaction volume is contained with all of it, then it's essentially the average of all these, and we get a poor pattern, basically an average pattern that makes it very difficult to index. So the things that affect our spatial resolution are going to be the spot size. So if you're having trouble from a resolution point of view, you'll want to decrease the spot size, which really usually means you're decreasing current. If you're decreasing current, you're going to have less electrons hitting that phosphor screen, and it's going to take longer to build up a pattern. And so that could be one challenge you may face. The other thing that might affect it is voltage. So voltage, if you decrease the voltage, you get a smaller interaction volume as well. But there is a limit to that. What we have found is that we find it seems to affect the depth resolution more than the in-plane resolution of the sample. Not entirely sure why that's the case, but we've observed that. Obviously, your material and its state will affect your resolution. If you've got deformation, it's going to make it harder. Higher Z materials are better reflectors. You'll need less current. You can get better patterns. Now, I did mention that if you lower the current, you lower the spot size. The microscopes will tell you, oh, no, you don't do that. But we've all seen it, and I think we all know that there isn't a correlation. But as you lower the current, that also means that you're going to slow down the collection of EBSD. And as you slow things down, it means if you have a sample that's drifting, drift is going to play a bigger role. And so there is a trade-off between speed and drift and resolution. So sometimes actually working faster will give you better resolution if you have especially if you have an insulating sample where you're getting any drift. So there is a trade-off there. Sometimes you want to lower the current, sometimes you need to increase it so you can go faster. So these are all things you're going to have to play with as you try to acquire good data. EBSD can deconvolve mixed patterns. So if I have the diffraction volume containing two different grains, as in this example, then I have the diffraction volume here, or the diffraction pattern from the red grain, diffraction pattern from the blue grain. As I'm at the grain boundary, I'm going to get a mix of those two. But the way EBSD works is it will try to detect bands. And so in this case, I set it up to find 6 bands, which is not very many, but good for this example. So I found 4 for the red and 2 for the blue, and so it's going to index the pattern as if it were the red orientation. And so EBSD can deconvolve bands at the edges. So a little also thing we've learned is that if we're having problems where we're smearing across grain boundaries, if we detect more bands than usual, that can also help us get a little bit better spatial resolution. Just to show you an example, we generally think we've got to have multiple points of the same orientation so that we know we've captured a grain. In this example, the smallest grains are about 20 nanometers in diameter. Now there are some that may be 8 nanometers, and I've made them white here. Those may be real grains, but it's hard to say. It's hard to trust those results. Unless we go back in and look at the patterns for those. And that's probably about, so usually what I tell people is anything bigger than a micron is pretty straightforward. As we start to drop below a micron and down into the 20, 30 nanometers, below 50 nanometers, it gets to be a little bit more difficult. And a lot can be done, and I'll talk later about TKD, which is a technique we use to try to overcome some of the spatial resolution issues. The other thing that affects our patterns are the SEM conditions. So the probe size, we can get, with a field emission gun, we're going to do better than a Lab 6. I don't see Lab 6s anymore much, than we can with tungsten. So luckily EBSD and field emission microscopes kind of grew up at the same time, so we get good resolution with those. I've already mentioned the current and the voltage effects, and vacuum as well will affect our results. In terms of the actual camera, you have things like exposure time and gain that you can play with. This is an example of 0.6 nanoamp beam current at 4.5 seconds, 1.5 seconds. You can see we've got a higher current, and here we have even more current. So we can go a lot faster, and the pattern quality is the same. Changing the gain on the camera, it can also help you speed things up, but it introduces noise into the patterns, and so you can only do so much by increasing the gain. This is just an example of that. So minimum gain, mid-range gain, maximum gain. You can see there's starting to be a bit of noise in here, even though these are all still really beautiful patterns. This is something we learned the hard way. So this is operating at 300x magnification of the microscope. We look at 2 points. The patterns are pretty poor. If I go to the same 2 points, and we could tell, as you can see, there's some contamination, then at 3000x, now we can see these patterns clearly. And this is because we talk about a stationary beam, but there's really no such thing as a stationary beam in the microscope. It's always oscillating slightly. And those oscillations are, the size of those oscillations is a function of the magnification. And so while it would be nice if we could work at low mag and have a stationary beam, we can't really do that. We're going to have to work at higher mag to work with smaller grains. And this is just an example. So here's a microstructure we did at 100x. You can see we're not getting anything in between these big red grains. If we go to 2000x, we start to see this. There's something there. It's not just noise. If we go to 10,000x, we can actually reconstruct the microstructure. So sadly, we can't operate at a low kV and pick up that and the big grains at the same time. And that's why I showed that example from the meteorite. We might have to do small, if we want to really capture this whole microstructure, we're going to have to do a beam scan, shift it a little bit with a stage, do another beam scan at high magnification to reconstruct and stitch this all together. Just another example, I think from a different meteorite. Meteorites have big grains, so we're always having to use what we call combo scan to do those. And so you can really see the individual scans here that we've used to reconstruct the microstructure. And so you need to think about this, how you're going to do this kind of process. Now I want to get into the indexing, and here's some references. I'll leave, by the way, I know you're taking notes, which is great, but I will leave PDF versions of the presentations here so that you can have some of these details, because I'm going too fast to write every detail down, I'm sure. But hopefully that will be of use to you. So these are kind of the main papers for this next part of the presentation. This is kind of the key paper where we really figured out how to index the patterns. The Huff transform, which I'll talk about, the first application in EBSD was by Krieger Lawson at RISU in Denmark. The confidence index, which I'll talk about, is from my colleague David Field, who's actually here right now. I think he's in Bangalore right now at IISC. A lot of this is in my thesis if you really wanted to dig into it, but here's another key paper from our group on EBSD. So I mentioned David Dingley's manual system, and in that you had to be familiar enough to identify different poles. So you had to know this was a 111, that was a 110, and that was a 112, and you click on those points and it would index for you. And so you could do it, and this is how the first systems were done by hand. But to do that, these are really nice patterns. Those original patterns we got on that system looked more like this, so it was really challenging. But with a little image processing, we're able to do a lot better. And the idea behind, the biggest thing in image processing is what we call static background correction. The idea here is you get a pattern from a single grain, an individual grain, and you get a background from very many grains. So something like 25, actually about 500 would be really good. And what you then ended up is the average pattern over all these grains is just a smooth background. And so now you're able to subtract that from this, and you're able to flatten this intensity gradient across the pattern and homogenize it. And you're able to get this kind of pattern here. And with that, then, we can start to do some indexing. There's another way to do this, and that is to use the pattern itself. So here's the pattern from individual grain. We blur it, and then we subtract that. And then we get this nice pattern here. This is good if you have multi-phase samples where the diffraction intensity differs from phase to phase, or maybe you have very rough samples where the gradient is moving a lot from point to point because of the rough surface, then you might want to use this dynamic background correction. It is quite a bit slower because you have to do image processing on the fly for each grain, or for each point. So I wouldn't use it unless you had to. But in those cases, it can be quite helpful. There's a lot of other things you can do. This is done automatically in the software, some of these histogram normalization techniques. But there's a lot of different things that are in the software you can do. I really don't do those unless I'm trying to publish a nice, one beautiful picture. When I'm doing EBSD, when I'm trying to do a scan, I'll just do background correction, and that's it. So how do we find these bands? We typically use something called the Huff transform, and this is an example. And the idea here is we're reducing the problem of finding a line or a band to finding a peak. That's why we do this Huff transform. And the way this works is for a pixel, you can think of a pixel here in my pattern. There's an infinite number of lines going through that pixel, right? And you can define each one of those by an angle and then the distance from the origin of a normal to that line. So for this red line, I get one rho theta pair. For this orange line, I get another rho theta pair. For the yellow line, I get another rho theta pair. And if we do that, we basically, the lines, or a pixel becomes a curve in Huff space. It seems like we're making it more complicated, but trust me, it actually will work. If you have a set of pixels on a line like you show here, what you find is that the curve for each one of these pixels intersects at a point in the Huff space. And that point then, what we're going to do is for each pixel, on each, we're going to create, the Huff transform is essentially an accumulator array. We're summing up the intensities of each pixel along these curved lines. And since those curves all intersect, and you'll get a peak in Huff space there. So we've reduced the problem of finding this line to finding a peak. So this is actually using our software. And I put this image in, and I get these set. You can see the individual curves for each pixel, and you can see the very bright peak where they intersect. Now, if I actually have a line, you can see it forms this characteristic shape. We actually call this a butterfly, and this becomes important later. Now, strictly speaking, I've done some research on this. The Huff transform is what we call this. The Huff transform is related to the radon transform. The radon transform is mathematically more elegant, whereas the Huff transform more of a discrete image processing way of thinking. And medical folks tend to use the radon transform, and image processing guys tend to use the Huff transform, but just in case it comes up. So I mentioned this butterfly shape. If we go to this picture now, you can see how these real bands still produce these butterflies. It's really obvious with this one. Now the butterfly shape is, you can think of it in the intensity like this. We can do what's called a convolution mask and apply that to, so this is the raw data. We apply this convolution mask to it, and it highlights the ones that have this characteristic butterfly shape. And so it creates this, this transform here, and now we really can just look for peaks. So we use the transform to find the bounds. Now what do? Well, this step we call indexing. And the first step is to build a lookup table of interplanar angles. So we know which bands or planes in our crystal are likely to produce bands, and we need to identify those. In this case, it's this set here for an FCC material. We determine all the symmetrically equivalent versions of those, and then we form all possible pairs. And from all possible pairs, we calculate the angles between them. So, for example, between a 200 and an 020, it's 90 degrees. So if we had these two bands in our pattern, they should intersect at 90 degrees apart from each other. We throw out the duplicates and sort it. It's all done in the computer. You don't have to know any of this, thank goodness, okay? This is all done in the computer. So now we get two bands. Our Huff transform has found this red band here and the yellow band here. They form planes when we bring them back to if we bring in this point here at the origin. And so we look at the plane normals, calculate the difference between them, and then we can see how those fit into the lookup table. So let's say this angle here is maybe 32 degrees. Well, then the red one could be 220 or 311, or they could both be 311s, or one could be 111 and 220. We don't know if the red one's 220 or the yellow one's 220. That part we don't know yet. But if we use what we call triplets, then we can do that. So for example, if this red triplet here is a 54.7, that means this is a 20 and that's a 111, or vice versa. But if we throw in this one here at 58.5, we know this has to be a 111 because those two match. And we do the same thing down here for this one. and then we know the orientation. So with 3 bands, we do know the orientation. With 2, you could do it with 2 if you could really identify the widths. But the Huff transform is not very good at finding the widths of the bands. So we use 3 and just use the angles. Because the Huff transform is good with angles. We can get angles within probably 2 to 3 degrees. And like I said, we can get those within, say, 2 to 3 degrees. This is if I use a tolerance of 5 degrees. You can see there's 4 possibilities for the red, 4 for the blue, 2 for the green. But if we apply our triplet argument, then we can reduce that quite a bit. In fact, there's only 3 possible solutions for these 3. This one, and this one. But you can see this is the right one. This one, while our 3 here are somewhat close, you can see other bands like this blue one are nowhere near close. Same thing here. Our triplet's good, but that blue one's way off. So we're able, if we break our detected bands into sets of 3, we can do this properly. So here's our sets of 3 and how many triplets you get. So if you detect 9 bands, you get 84 triplets. So there's a lot of data there. And this is then how we do it. We use a voting scheme. So right here I have 5 bands. I have, I think, 10 possible triplets. The first solution appears 10 times. We get a second solution that appeared once and a third solution that appeared once. And so this is our most probable solution according to our voting. And so you can see here it fits nicely, and it does a great job. This is the second solution here. In this case, only the red, yellow, and magenta bands match. So these 2 do not match. It's only these 3. And so that solution didn't do as well. Now, you can then go back and see how well you match. So this, if the bands match well what we detect, I get a low quality fit, we call it. If the fit is large, that means it's a bad. So you can see these bands don't detect very well. And this has to do with how well does the Huff transform working. It has to do with some calibration parameters, which I haven't talked about yet, but we'll get to. And an important thing of this indexing idea, this triplet indexing idea and these voting, is we can calculate something we call the confidence index, or CI. And the confidence index is equal to the top vote getter minus the second highest number of votes divided by the ideal. So the ideal in this case is 10. The top vote getter is 10. And the second highest is 1. And so this would have a confidence index of 0.9. Now if you think about this, let's say we have 2 solutions that are really close to each other, and it has a hard time finding the right answer. Then we would have a confidence index of 0. It doesn't mean we got it wrong. It just means we have a 50% chance that we got it wrong. And so a confidence index of 0 isn't necessarily mean that it's wrong. And in fact, I went in and did a study where I took a scan like this, added noise to the patterns, and then tracked the indexing as with increasing noise. And what we ended up with is a curve that looks something like this. So you can see when the confidence index is 0, we're actually still above 50% correct indexing. But if we go to a higher confidence index, you can see as I get to 0.1, in this case, it's about 99.5% correct. This one's a little stronger than usual. I've done this with a couple of different materials. And generally, we find that if we're at about 0.2, we're usually around 99% correct. So if you're doing a scan and you get a confidence index of 0.2 on average, it doesn't mean you throw away your data, okay? Look at it closely, and I'll bet that probably 95% of it's probably good data. So a confidence index of 0.2 and above usually means we're almost near 100% correct, if you will. Although with a multi-phase sample, this will probably shift a bit. I already mentioned the deconvoluting patterns, and you can see this effect in the confidence index. So this is the confidence index here. Now, when you have mixed patterns, now you have 2 solutions competing, and so your votes will be affected by that. And so here, you see the confidence index at the boundary edge is 0, even though really we've only missed 1, 2, 3, 4, 5, 6 points. Our confidence index drops And we have ways of kind of dealing with that in the software. The angular resolution is, there's a couple different ways to measure this, but this is from a single crystal, a millimeter by millimeter scan. And so if you look at the pull figure, it looks really good, but if you zoom in, you can see a lot of these points now are kind of clustered around here within about a half a degree away from the center. Well, this is a half degree, so really about 0.25 degrees away from the center. And so this is the distribution here. So the angular resolution, there's different ways you can describe it, but typically we can get down to about 0.1 if we're really, really careful. But I would say probably 0.2 to 0.3 is probably more typical. Now the angular precision does decrease as we use what we call binning to increase the speed, and I think I talk about that later. So if we bin it a lot, we can increase the speed, and so this is kind of increasing the speed here. No, this is higher speed here, lower speed down here. And you can see then the misorientation or the angular resolution drops. And so if you really need really good results, don't try to rush it, and you might have to slow down a little bit. All right, so I mentioned naming. There's been two names for this technique. We call it transmission Kikuchi diffraction. I would say this is winning in the community. So if you publish a paper using this technique, I would probably call it this. Otherwise, your reviewer is going to knock you for this one, and you're going to have to redo your paper. But there are a few papers that still get through with this name, TeBSD. And this is work that Bob Keller and Roy Geist did at NIST in the United States. I'm using a sample from my colleague Suzuki-san in Japan. The kind of classic paper on this is a paper by Pat Trimby in 2012, and I think he used the words TKD, which is why it's become popular. They called it TeBSD because they used the eBSD system to measure it on a transmission sample, and I'll show you how that works. So you should know how transmission Kikuchi patterns are formed. You have it's an electron beam. Those that satisfy Bragg diffraction produce an excess line and a deficient line. And so you get patterns that look like this. And so this is a TEM diffraction pattern, Kikuchi diffraction pattern. Now, in a TKD pattern, transmission Kikuchi diffraction in the SEM, you put a transmission electron sample in, put your electron beam in, and now all your diffracted electrons are coming down below the sample. And so we can put it in here in a lot different orientation than we did with eBSD. So now we just have a small tilt. 40 degrees is actually kind of atypical. It's a lot. And we look at the diffraction pattern that's formed here. This is just a sample holder, so there's a little transmission sample right here. It's mounted here so that we're at a reverse angle. So eBSD, the angle is like this. It's actually about the same as this. And transmission, now we're rotated from that. So if you do that, this is at 20 degrees, 40, 60, 20, at different thicknesses and working distances. So here's the kind of patterns we get. They look a lot like eBSD patterns, although they do tend to show a little more distortion in them. If you look very carefully, that's very thin at the top and a little thicker at the bottom. That's actually more obvious on this one here. But we can do eBSD then in a transmission mode, essentially, or we can use our eBSD detector on a transmission sample. Now, if the sample becomes really thick, you'll see we get a reversal. Instead of the bands being bright, they're actually dark, so we get an intensity reversal. And sometimes in a single pattern, you kind of see it here, you can get both bright and dark, which really causes trouble when you're trying to index them. Now, the important part here is where is this pattern formed? You have incident beam, you have diffraction as you go through, or scattering. But the important thing is the actual signal is created here at the exit edge of the sample. And you can see that here. So here's eBSD, and this is the front surface. This is if we did the back of that same sample in eBSD. And then this is TKD through the front and out the back. So you can see this one matches this one much more closely, although there are some differences. You can see here and some subtle things here, where this grain actually goes all the way through the sample. So that's another important thing is the TKD it's from the back edge of your sample when you put it in. Here's an interplay between sample thickness and voltage. So this is a 15 kV and 25 kV. So in the very thin sample at 15 kV, we image this really nicely. If we go to higher voltage, we don't image this very well, but we image this very well. So it can be a good idea to do your sample. If you're having problems with the uniformity of the thickness, you could run it at 2 different voltages and merge the data together to get one good comprehensive picture. This is just an example from Suzuki-san and the sample that he had. So this is a TEM bright field image, a TKD IQ map. You can see the similarities. An EBSD IQ map and an SEM image. And it's somewhat similar there. So it's a nice sample because you're able to do it both ways. So you have to remember we have to do a kind of a mirror because now we're looking at back samples. And so you need to be careful with that. But the software will correct for that. So you shouldn't have to worry about it. But the beautiful thing is now we're able to index these carbides right along this grain boundary edge. And so the smallest particle is 30 nanometers, but this is getting pretty old. We can do things down around 10 nanometers or even smaller, maybe even down to 5 nanometers with transmission EBSD or TKD. All right, right on time. Are there questions? So this TKD is done in an SEM. Yeah, so it is possible. You have to have a transmission sample, but you do it in the SEM so you don't have to go to the trouble of putting the TEM. But you do have to do all the preparation, which is frankly the hard part. There are techniques out there to do orientation mapping in the transmission electron microscope. There's a group called Nanomegas that sells a system that does that. But this is using our existing EBSD system, so you don't have to buy a whole new system, but using a transmission sample to get high resolution. I know a lot of the people who are doing transmission frequently are using fibs, so that they can control the thicknesses a little and get more uniform thicknesses. I don't know, I think the group here is doing quite a bit of TKD. Has anybody else done DKD here? Yeah, what kind of thicknesses are you using? Sorry? 80 to 100 nanometers. So, thank you. I know this institute's doing quite a bit of TKD, which is impressive. Any other questions? It's not fair to ask for questions just before the break, right? It's should ask for questions after the break. I'm sorry, the air conditioning's making it hard. Without using the Kikuchi map? So you want to do just regular? I'm sorry. Oh, transmission imaging? Yeah, so you can do it with regular Kikuchi diffraction in the TEM. Actually, they use spot patterns. And it's a template matching approach. It's a system called A-Star from this company called Nanomegas. So if you look up A-Star or precession, the technique is in the literature is called PED. So precession electron diffraction. And so they have some hardware in there to increase the solid angle. If you just did straight Kikuchi diffraction spot patterns, you don't sample enough of reciprocal space to really get a good indexing. But with the precession technique, you're able to get enough spots to be able to index it. And that's the name of that technique. So if you're interested in that, I can point you in the right direction and give you some papers. But that's not something we do. Right. There are.
So where are these electrons going? What happens to the sample electrons create the system? So will the pattern be same after doing a scan minus the detection rate scan minus the
Yeah. So sometimes the sample's destroyed, right, with the signal. And so I'll talk about this, I think this afternoon, as we're working on a new camera which uses direct electron detection. And the idea there is that we can work at smaller voltages, smaller currents, like picoamps as opposed to nanoamps. And then we're able to hopefully be able to analyze more beam-sensitive materials. There are a lot of signals coming off the microscope. With EBSD, we primarily are looking at elastically scattered electrons, or the ones that are forming the patterns, although that we know now better the distribution of electrons and the energies that we're measuring, and there is some inelastically scattered electrons help form these images. But the images themselves, in terms of the way we interpret them, we basically assume we're only dealing with the elastically scattered electrons. The other signals, like EDS, are coming off the sample, Auger, other things like that. We can do EDS simultaneously with EBSD, but we can do forward scatter or back scatter simultaneously. But it's difficult to do a lot of the other techniques, for example, WDS or CL, because it's with the high tilt, a lot of the geometries become very difficult for some of these other techniques. And so what we've done there is to take, if, for example, I've done an example where we wanted to look at the WDS signal, or use WDS to look at the X-ray signal. And we did that flat, and then did our EBSD tilted, and then correlate the two data sets together. Now, you bring up a really good point about the TEM, and that is because if you want to do EBSD and TEM together, sometimes one, as soon as you hit it with the electron beam, you've destroyed the sample and you can no longer use it. And so that's really difficult, and I don't have a lot of good answers except to work at lower voltages and lower currents. And so I guess make sure if you're doing that, you'll have to do the least aggressive first, but that may not work. I know that can be a problem. I know for these TM examples, sometimes what they'll do is they'll use EBSD because it's low voltage compared to the TEM. Do the samples in the SEM, do that orientation work, and then take it to the TEM to do their imaging work after the fact, because it's hard to do it in reverse. So yeah, I'm trying to think what else. Yeah, it's a difficult thing, and I'll talk about, like I said, this new camera we're working on, which I hope will help solve some of these challenges.
But to magnesium and difference.
Yes.
Why it is happening?
I think the magnesium, are you getting microtwins in your magnesium possibly? I know that's one of the challenges with magnesium. If we get too much deformation in it, then we get...
It's not deformed.
What's that?
Just as cast.
Oh, so non-deformed?
Homogenized.
So how are you preparing the samples? I know when we do magnesium, we tend to have to finish with the ion beam. We can't. It's really difficult to get one through just straight mechanical polishing. And so now we'll have, you can't do it in water, and so we have to do it in oil or alcohol, and then after that. But even with that, we found that if we finish with we use a broad beam ion polisher, very light. If we hit it with that as the final step, then we get much better results than if we don't. So other than that, I don't know what to tell you, other than good luck, because magnesium's a hard one, especially if it's deformed, because then you're introducing twins, and if those twins get small enough, then you're going to get mixed patterns, and then you have basically a resolution issue. Okay. All right, shall we break?
In your presentation, you told some material is easy to find with EDS and some with EBSD. Can you elaborate in your lecture later? Or?
Some materials are easier than others. Easy materials are heavy, so tantalum's easy. Aluminum can be hard, but if you electropolish aluminum, you can usually get good results. The other problem, and aluminum is actually a good example, are materials that form oxides. So if you have a material, you polished it beautifully, and then you put it on the desk to put it in the microscope the next day, all of a sudden there's an oxide film and it's your history. So if you've got materials that form really, oxides really quickly, or intermetallics and things, then you may need to put them in a vacuum, before you index them. If they're really fast forming, then you might have to do it. Then I would really recommend if you had a dual beam, like if you had a fib, and you could take off that layer and then put it into the, put it underneath the electron beam and do your indexing. But yeah, it's usually light materials are a little harder to do. Soft materials can be hard to do. Like pure lead is difficult because it's so difficult to deform it or to polish it and get rid of the deformation. And so in that sense, brittle materials are sometimes easier to do. Multi-phase materials are also harder to do. So if you have a soft phase and a hard phase in one material, how do you polish it? You're very likely to destroy it. And once again, broad beam ion polisher helps with that problem. The other thing that we have done, and it's really difficult, is to polish it and do one phase and then polish it for the other phase and then try to match the two pattern scans together. That's really difficult to do successfully. But I would recommend, I don't want to be a salesman for the broad beam ion polishing companies, but they really are helpful for these most difficult materials. So I'd recommend you touch base with one of those. Like I said, in our lab, we do most of our work. We don't have a certificate to do electropolishing, so we can't use aggressive chemicals. So we do everything mechanical, and then with a broad beam ion polisher at the end. But for mechanical, it's very important to do your polishing as your instrument's set up for. So I've been into polishing labs at universities where, when I was a student, we got one sheet of 240 grit, one sheet of 1200 grit, one sheet of that, and after we polished our samples, we hung those up on a clothesline for them to dry to use the next time. That will not work. That will not work at all. You have to, the manufacturers recommend 30 seconds maximum, and we have found that is really true. They're not trying to sell you papers, polishing cloths. They're really trying to help you get better results. And so the cutting is really good at the beginning, but after 30 seconds to a minute, it's really gone. So don't sit there and try to, longer is not better. It's better to do each paper individually and do it quickly, and then go to your cloths. And you might find playing with a nap on your cloths can help the hard, soft phase problem as well. And then we finish, like I said, with a colloidal silica on a vibratory polisher, and that really produces good results. And we'll go as long as 4 hours on that colloidal silica. And you may need to, depending on your sample, you may need to adjust the pH of your colloidal silica, but generally we just use the standard and we're fine. So just my advice is don't skip steps. Really, the manufacturers really are quite good at their recipes, and we've learned a lot from them over the years. So, and they've learned some things from us too, because they were taking shortcuts they didn't know hurt their results as well. But you can really see it with EBSD, and you can't see it with an optical or a secondary electron image. So just follow the procedures, and you will get patterns. All right, let's take a break. I'm losing my voice, so let's take a break. Started? Okay. Welcome back. I'd like to talk about data acquisition this afternoon, or this morning, I guess we're still morning, technically. And tomorrow we'll focus more on what to do with the data. So today we'll focus on collecting the data, and tomorrow we'll focus on what to do with it. So I'm going to talk about some of the new stuff we've been doing. I think this is actually an exciting area. And those of you who are familiar with EBSD, you'll see lots of new stuff. Those of you who aren't, some of this might kind of not be applicable, but eventually you'll get there. So first off, I'm going to talk about the detectors. We have two new detectors. One is called the Velocity. It's a high-speed CMOS detector. That's what is currently here as of 2 weeks ago, or so yeah, it's only been here 2 weeks. So it's one of the newer systems around. And then I'll talk about something we call direct electron detection, which I'm excited about, which is a completely different approach than the focus we've had over really the past 20 years, which has been all about speed. And then I'll talk about some new things in terms of indexing that I think are exciting, that hopefully will be helpful to you. So this is our new high-speed CMOS camera, Velocity. It comes in, also called Orion, and comes in different flavors and speeds, but I'll just focus kind of on the high end of it. Okay, so signal detection really is the same between CCD and CMOS detectors. So CCD cameras are, oh, I don't have my phone, or what's in your phone. Or no, CMOS is what's in your phone. And CCD is slowly disappearing. There are still applications. They're still used in some of the really high-end telescopes and things like that. But because we're all using a phone and we're all taking pictures of our kids and, and our friends, it's dominating the camera world. And so CMOS has gotten much better, and it's gotten much faster. So the reason for the speed has to do with the amplifiers. So this is a CCD chip. You have the sensors. They go through a gating process. The signal comes in. It goes down a register. And then all those signals are amplified. And you create an image. And so they transport the charge row by row, and then they go into this one amplifier. And then there's an A to D converter that turns this array of charges into an actual image, a digital signal. And it produces very high quality, low noise images. With the nice thing is the amplification is the same across all the pixels. And that has certain advantages. But it does limit the maximum readout speeds, which is typically 20 to 40 megahertz. Another thing that it does is we can bend the signal before we even send it through amplification. And that's one of the things that enabled us to use CCDs and get to the speeds that we are able to get to. Not as fast as we can with the new CMOS, and I'll explain why. But still, we've come a long ways with that. Binning basically improves the sensitivity camera because you're basically taking, the idea behind binning is you have all these pixels, and then you group them into groups or bins of pixels. So we take a 4x4 array of pixels, so 16 pixels, and reduce it and turn that into a single pixel. So it really increases the light gain or light gathering capabilities by a factor of 16 if you use a 4x4 binning. And so you can operate like this, and you can see we have a 480 by 480 chip, but we typically, if you bin that by 4, you get to 120 by 120. If you bin it by 5, you get to 96 by 96, which is a typical condition we use for EBSD. And there's a very good signal-to-noise ratio because we only have the amplification noise once. CMOS is a little different. The idea behind CMOS now is we put the amplifiers on the individual pixels themselves. So those are the amplifiers. So the nice thing is this speeds up the process considerably because you're doing the amplification process in parallel. And you can read out the things at a full resolution much faster. So one challenge is that the amplification is not identical, but because of our cameras, they've gotten very good at this, and so we can operate that way now. So it's less, because of this, there's really no advantage to signal binning like we're used to, even though we do a little bit because we can affect the readout speeds. But you can operate really fast. So this is a typical arrangement of the system here. We have our electrons coming in, hitting a phosphor screen. There's some lenses involved and then a camera to detect that, and out comes the intensity. So the nice thing about CMOS then is we can go really fast at much higher resolution. So for example, here at 4,500 points per second, which is our maximum speed at 120 by 120 pixels, we get a beautiful pattern like this. Once again, this is our test samples of nickel. Here it is on a CCD sensor. The fastest we could get to is about 1,400 points per second, and that's at 30 by 30 pixels, so much less resolution, pixel resolution. So that increased pixel resolution does bias some things. It can help us with improved band detection and especially with orientation precision at fairly high speeds. So it's 10 times faster than the CCD at the same pixel resolution. Like I mentioned, there's different models of it, and the Super goes up to 4,500 points per second. It's a high-speed, low-noise CMOS sensor, and we've optimized it for EBSD conditions. It's actually 640 by 480, but we only use a square part of it, so 40 by 480. So it's really ideal for situations where speed is critical. A good example is in situ work. Maybe you're trying to recapture recrystallization like I showed before, and you know, we went as fast as we could on that, but we're missing intermediate steps. So, you know, in fact, while it's scanning, recrystallization is happening. So we might have a different rate of recrystallization at the top of our scan than at the bottom of our scan. And so this high speed will allow us then to capture that. If you're doing 3D where you're doing serial sectioning and many, many sections, it can be useful. If you're doing the mosaic scans I showed before, or we're stitching lots of scans together, it's helpful in that situation. And this is just an example. This is 3,000 index points per second at 11 nanoamps. So on the plus, here's the IQ map and inverse pole figure. You can see we're getting great indexing, basically 100%, really rapidly. And the challenge now is we're collecting so much data. So we're having to rethink some of our analysis routines because the amount of data we're collecting is so much more than we're used to. This is at 4,500 points per second, and you can see there's no change. It's still perfect indexing, basically 100%. Here's something a little more complicated. It's additively manufactured nickel and superalloy, but you still see we're getting really good results. The one thing you will notice is that we're operating at a little higher currents. We're at 30 nanoamps to get these kind of speeds. We're going so fast, and the light, you know, the phosphor, we need light from the phosphor, so we're having to hit that phosphor with more electrons to get these kind of speeds. So if current is your limiting factor, this is probably not the best camera for you. Our previous Hikari will work fine. So this is just to show you how fast this actually happens. I hope this works. So you can see this scan is happening basically at slow scan SEM imaging rates. It really is. You're collecting all this data so quickly that you can get a scan like this that fast. And you can see the indexing is very good. This is the orientation data in color, and then the grayscale. Behind that is the pattern quality. And like I said, that's pretty similar to running your SEM in a slow scan mode if you're looking for a really good image. So that took 40 seconds, and we collect 180,000 data points, which just to let you know, when I first did my very first EBSD scan, we had a $150,000 computer, and it took 4.5 seconds per image. So we thought that was amazing, and we were so happy. And now we can do it in 2-3 orders of magnitude faster. A deformed steel, just to show you can deform metals, even though we have the higher beam currents. We still get great indexing success rates on this. This is 1 million data points. And just to show we do capture the subtle changes in orientation, even at these high speeds. This is within this 1 grain here, and you can see we are capturing these low angle misorientations. The orientation precision is very similar to what we do with the CCD cameras. In this case, this is great. We've got a less than 0.1 degrees. The average misorientation in this 1 millimeter, I don't know how big this scan is, maybe 10 micron by 10 micron scan, it's 0.04 degrees, which is terrific. And that's partly because we're working at a little higher resolutions. Another deformed sample. This is 30% cold rolled brass, and we're still getting great samples off the camera. And here's our I haven't talked about this, but this is a kernel average misorientation maps, which is a way of capturing deformation in the sample, and you can see we can capture that at these high speeds. This is a titanium wire before bending, and you can see it's great results. And then after bending, once again, great results. The indexing success rate was 87%, but we've got some area out here that we're not even using. That's off the sample now, and we're getting some voids in here cracking, so not surprising. This is an aluminum friction stir weld. This is a nice example because we have these large grains here, small grains here, and 7 million points to capture this bimodal grain size. And it comes out well. This is a dual phase material, just to show we can do that. It's a pretty easy one, BCC and FCC steel sample. And once again, 2 million data points, just, quickly. We can do simultaneous EBSD and EDS. With the silicon drift detectors we have today, we can operate now at similar speeds and get enough counts to do it even at these high rates. So this is just to show you, this is a battery, and we have, I think, nickel out here, no, copper out here, nickel in here. And you can see this is basically the EDS data. So, works well. So that summarizes the high-speed camera, and we'll see a demo of it this afternoon. So not too much to say about that. What you won't see is this detector, direct electron detection. This is what we are calling clarity. And you can see from this pattern the amount of detail that is in these patterns. And the focus now is, instead of it being on the actual mapping capabilities, the focus is actually on the patterns themselves. So a little history. I mentioned Venables and Harlan in 1973 in the SEM. What they would do is mount a little holder, film holder in the microscope, and put film in there, Polaroid film, and hit it with the beam, and then they capture a pattern that looks like this. This is actually one done on that original system by Bobby Kishi, one of David Dingley's students. The next step then that David came up with was to put an analog TV camera in there. That was the image I showed earlier. And now we've introduced a phosphor screen, lead glass, a lens, and the camera. We've been able to take out the lead glass to a certain extent now. This is another example of an analog CCD camera now by Joe Michael. This used a YAG crystal instead of a phosphor screen. And then we started using SIT cameras. TSL when we first started, and we had a lead glass. And then we went to CCD cameras. I should say the lead glass now, we can take that out because we put the camera inside the chamber itself. And now I just mentioned the CMOS, but still we've got all these issues. And the focus has been on speed. So the CMOS was there because of speed. The very first camera we worked with, like I said, was 4.5 seconds per point. We're already up in the points per second at that point. But you can see the speed has really gone way up now. We're at 4,500 points per second. And before long, we're going to reach a limit where phosphor screens and probably the decay times are going to get us. But we're still a little ways away from that. So this is how long it takes to collect. So if we use 1 hour to collect a map, we can collect a 16 million point map now today in an hour, which is just amazing. But the optics are great for what we're trying to do. When we're trying to go fast, we're trying to get patterns as fast as we can. But they do introduce certain things. We have distortions due to the optics. It could be a barrel or pincushion, usually the pincushion. You have aberrations and astigmatism due to multiple lenses being involved. You try to reduce that as much as possible, but it is there. And so you have those. You also have scintillator screen effects, depending on what kind of scintillator you're using. We've used 2 different phosphors over the years. We know they're not perfect. We have grain size effects due to the pixel size of the phosphors. We have thickness variations in the phosphor, which affects the voltage sensitivity, and phosphors produce something called smearing. We also get some light loss in the lenses, or if you use fiber optics, you also get some light loss. So as light goes through those lenses, some of it's lost. So the direct electron detection takes care of a lot of that. The idea is that we're actually detecting each electron and counting them individually at each pixel. So this is the first one, or one of the first ones in the literature. The first work on direct electron detection applied to EBSD was done by the University of Strathclyde group in Glasgow, Scotland. But you know, direct electron detection is new for EBSD, but if you work with TEMs, they've been around for quite a while. They are expensive. Those of you who haven't owned a TEM and have bought a camera, they are expensive. But they're expensive for a reason. That's because they give us some real advantages. So our goal with direct electron detection is to remove the optical path. Like I said, it's been used in the TEM for biological specimens too. And it has been demonstrated to work, but on a one-off kind of laboratory basis. So the challenges we're facing are cost, the sensor, trying to get the geometry right, trying to get it in close enough that we get good solid angle, and also temperature, dealing with heat buildup on this sensor. So we developed one for EBSD geometry. It's four 256 by 256 Timepix chips, and that produces a single 512 by 512 sensor. And we're able to do, originally we weren't sure we could do this, but we are able to do it with passive cooling. So there's no vibrations due to a fan or something like that, which is great. There's just a picture of the chip itself. If you really want to see it, there's a website devoted to Timepix chips, and you can read about them. So direct electron detection, this is what the camera looks like. I've drawn the sample on here that way just so you can see it. But it's actually a CMOS detector, and it's just that we no longer have the phosphor. We're going directly to the detector. So a charge comes in, it goes through an amplifier. We have to have a threshold to say we're only going to use this signal here so we don't pick up the noise level. And after you do that, you actually count. So you count 1 electron, 2 electrons, 3 electrons, and you just count electrons at a sensor. So here's standard EBSD mapping with a regular camera. Actually, I don't know why that slide's in there. So what I want to point out is we're actually counting electrons. So at 10, this is at 10 kV, 380 picoamps. There's 450 picoamps. In here, the highest pixel, or the pixel with the most counts, had 70 electrons counted. This one had 50. You can see it's a weak pattern, but there is a pattern there. If you go out here to 60 milliseconds, we've counted 380 electrons to get that image in the highest pixel intensity. And just continuing on out to 300 microseconds, or milliseconds, terrific image at 450 picoamps, 380 picoamps. And 10 kV, and all the way out to a full second. So the key is here is we are counting electrons. So we can use this and do a scan. It's not anything to get excited about because that's really not our focus, but just to show you we can do it. And this was, this is low current. I lost the labels. So here's the patterns, and we've had to do something called MPAR to get it indexed. But just to show you the quality of these patterns, this is nickel at 20 kV. This is 520 milliseconds on our Hikari, our CCD camera. This is the direct electron at 153 microseconds. And you can see the amount of detail here. You can see these causal rings. You can kind of see it in here, but they're much more spread out. You see a lot of detail in the poles. What you see here is the seams. Like I said, there's four 256 by 256 chips. There's one here, one here, one here, one here. And so you can see some seams that we're still working on trying to reduce. This is a ferrite, and just the amount of detail here, I mean, you can see multiple orders of magnitude that there's no way you can see with a regular detector. And we can index them. Now what I'm going to do is I'm going to zoom in so you can really see the amount of detail here. So this is pulling the detector back is the way we're zooming in. It seems backwards, but we're getting more detail because we're reducing the solid angle. And even with the detector this far back, you can see detail. So it's amazing. This is actually a simulated pattern. And I'll come back to simulation, but we're getting as much detail as we get in the simulated patterns. So it's really, these patterns have become helpful for really assessing how well our simulation's working. We're learning some things to improve the physics in our simulation models from these kind of patterns. And this is just zoomed up. Now we could do the we can do the simulation with more pixels to probably better approximate this, but it is, the detail's amazing. The other thing, we've always wondered, if you look at EBSD patterns, if you go out here to the edges, they're always a little weak. And we've always thought that was just had to do with the optics, or maybe the electron path to get there. And we weren't really sure if that was the case. But we do see it in these very highly detailed direct electron patterns. You do see the signals weaker up in the corners. And so we do know now that it's an attenuation of the signal from this longer electron path from the signals versus at the center. And so you're coming in at a different angle and you're smearing it across multiple pixels. And so you're getting some smearing effects. This is just showing you the impact looking at increasing atomic number. You'll see this is beryllium, way up in that top left corner of the periodic table, and we're still getting great results. And this is platinum down here. So this is like I said, we're working on this. We think it's going to be very helpful for beam-sensitive materials. I didn't have time, but I just got an email from one of my colleagues on Friday that we have a scan at, I think, 10 picoamps. And so, I mean, if you've got a beam-sensitive material, this might be a solution. And we think we can do some materials we haven't been able to do before. So we're pretty excited about it. It's not on the market yet. We're still working on it. The engineering tasks are big, but we're getting closer, and I think we'll probably have it probably first quarter next year. So we're excited about that. I want to shift gears now and talk about some of the techniques we're using to index patterns in new ways. And I'm showing, this work isn't all mine. It's from a lot of different people. I have my colleagues at EDAX. Matt and Scott and I are in Utah in the United States. Renee's in the Netherlands. Pat's in New Jersey. And Sean is also in New Jersey. Mark DeGraff and Saransh Singh are at Carnegie Mellon University, although Saransh has moved now to Lawrence Livermore National Lab. And I bring up Mike Jackson and Dave Rohrnhorst and his, I think, student, Patrick Braywick at Naval Research Laboratory. So I've done a lot of this, but I need to give a lot of people credit. So the motivation here is if we have really bad patterns, we get really bad scans. Seems logical, but how can we address that? It's actually amazing to me. This is actually a real pattern from this scan. It's actually amazing to me we can get this good of data with this poor of a scan pattern. But so EBSD, our algorithms work well. The Huff transform, the indexing does a great job. But we do get scans like this occasionally. And we have various cleanup methods that can take this data and create something like this. But there's a lot of interpolation going on here. And some of this data, you know, there's little funny things going on in some of these grains. The boundaries are kind of shaped kind of funny. And that's just artifacts from the cleanup routines that we use. But with the computers we have today, more and more people are storing each pattern. And originally we didn't do that. The computer speeds, it would slow down the computer, and so we didn't want to do it. But with a solid state detector now, or a solid state hard drive, and the computer speeds, we can save every pattern if you want. It does eat up a lot of memory on your hard drive really fast. If you do a 2 million point scan with a 120 by 120 patterns, you better have a good hard drive because it's going to fill up quickly. So we have some various ways of approaching this, and I'm going to talk about NPAR and NLPAR. NPAR is our group at EDAX, NLPAR is the group at Naval Research Lab, and dictionary indexing comes out of Mark DeGraff's group at Carnegie Mellon University. So we call this NPAR, Neighbor Pattern Averaging and Reindexing. The idea here is I have a pattern from a pixel, and I take the pattern from all the neighboring pixels and sum them together, and I get an average pattern for that. And it's a little better pattern, typically. And then I re-index it. So this does require that I save all the patterns during scanning. So here's an example, 130,000 points on a hexagonal grid. We're using 96 by 96 pixel patterns. And what I'm going to do now, so I can compare, is use a Gaussian, add Gaussian noise in fractions between 0 and 1 to these patterns. So we can make the reference scan in this case as the original scan without any noise, without any Gaussian noise added. So here's 0% noise, 50, 80, 100. So even with adding noise, we're able to index. I mean, this is pretty good at 50%, but we start to see the effects here and really seeing 100% noise. So now I apply this NPAR algorithm. So I take the pattern at a pixel, take the pattern from all the neighboring pixels, and average them together. And so you can see this is a big improvement in the pattern quality, and from something you don't see any pattern, you actually can see a pattern now. And so as scanned and NPAR, huge, huge improvement. And so we're using this to deal with sound when we have really poor patterns. And it really works well. It's really almost as because if you're using a hexagonal grid, you have this point and you have the 6 neighbors. It's like you're increasing the exposure time by a factor of 6. So you retain the speed that you had for one pixel, but by averaging in the others, it brings in the others well. And part of that is our ability to deconvolute patterns at grain boundaries works well, so we're able to do this. There are situations where it won't work, and I'll show you examples. So this is just some numbers to the last set of pictures. This is the indexing rate. As we add noise, it drops way down. If we add NPAR, it stays high, which is great. So now we thought, well, that's artificial noise added. Let's look at adding something that's a little more realistic. So we've done the same thing where we've collected a bunch of patterns, but now we're doing the same scan and we do the same area 10 times. But we do it with increasing gain. So we're increasing the noise in our patterns. We also increase contamination as we went, so we're getting more noise that way too. But you can see we're getting more and more noise, and our indexing success rates are dropping, and they stay high and then drop pretty rapidly. So this is just 4 of those scans, 0 gain, and then one's near the end. This is 36 is the maximum gain on our CCD camera. So you can see the pattern's not very good. With NPAR, we do pretty well until we get here, and then it starts to fall off. With some cleanup, we can reconstruct some of it. And so you can see there the results are good, but what it does tell us is that if our noise is more realistic, the NPAR doesn't quite get us as much improvement as it did when the noise is artificial. But one of the weaknesses of NPAR is we're taking 6 pixels, we're averaging the pattern, so we're going to lose fine details in the structure. And so if you look here at these 2 twins, they get smeared into one. Those 2 get lost. It's completely gone. That one gets lost. So it's especially problematic with twins, actually. It's the worst situation for this technique. And of course, we always do our first examples on nickel, so we saw this right away. So we came up with an idea of using, can we do some pre-filtering? Can we check the patterns and see if they're the same before we put them into our averaging routine? And so the idea was only to use patterns of similar type. And we do this, we have to come up with some way of doing this. So this is, as scanned, this is the NPAR, it smeared it. If we use this selective technique where we throw out patterns that aren't the same in our little averaging kernel, then we do pretty well. But this is on good data. If we go to poor data, you see hints of that second twin, but it really didn't do the job. So Dave Rohrnhorst and his colleagues at Naval Research Lab came up with this idea. It's called NLPAR, and there's a lot of math here. Don't be scared of it. Basically, the idea is there's a weighting. This is the key thing, is there's a weighting. It equals 1 for NPAR, but for this tech on NLPAR, we use different. So here's our raw pattern. We look at all the neighbors, and we come up with this difference scheme. And we're going to weight them now. So NPAR, if we did a big kernel like this, would give us this pattern, which is clearly a mix between this grain and this grain. if we do NL par now and we weight them, then these get weighted towards 0, and these, the one here will be 1, the one next to it's very similar. Ironically, this one down here is quite similar. It gets weighted high. So what NL par does is it gives us an advantage over N par, is it throws out different patterns, which allows us really to use even a larger kernel. So we get even more averaging. And so here's the conventional N par and L par with a window of 5 by 5. And you can see now we get that twin there. Oh, I lost, you can see here, those are still there. So it really does a great job. Okay, once again, beautiful patterns. How does it work on noisy patterns? So here's the raw pattern, N par and L par. And you can see by eye that's a huge improvement. And it's really quite interesting to me when I see this is there's grain, it's not uniform. I thought it would be, the weight would be, one here and then slowly go away, but it actually bounces around. It's not very uniform. But here's our conventional scan, N par and L par and dictionary. And you can see this does the best. So this is a great technique, but with every great technique there's a downside, and that's speed. This takes some time. So you don't want to use it unless you have to. Just to show now on a really difficult sample, deformed magnesium for our friends in the back. You can see this is very difficult. So this is after N par here, and then this is an L par. And you can see, so it's 54% indexing rate with N par 61, with NL par 64. I'll come back to these. So it does give us, 10% improvement over what we had before, but it's still a difficult sample. We can only do so much. Just to show you, this is as scanned N par. It's interesting to me, it's not exactly the same points that get improved. So we came up with a merging scheme, and we get even better results that way. Just to show you N par and some other samples, this is a brachiopod, a seashell. So here's without just regular data and after N par. And this sample came to us from Erika Grieshaber at Munich. And you can see, it's interesting to me, not only does it improve the orientation data, it actually shows us detail in the IQ map that we didn't expect to see. So what are my conclusions? N par is great. It works well. But it's due to, it works best if there's speed or noise from the camera as opposed to real challenges in the sample. And what that tells me is you can't use N par as an excuse for not polishing your samples. You still have to polish them and do the best job you can. So another approach to this problem, and I've already alluded to it, is dictionary indexing. And the key to this is dynamic pattern simulation. And this has been a big step. And I'll talk about this. We actually have built this into 8.5, which should be out by the end of the year. And so it's an add-on module into 8.5. We call it OIM Matrix. I don't know why, that's what we call it. So EBSD pattern simulation was pioneered by Emil Winkelmann when he was at MPI Halle, I believe is where he was when he did that work. He's since left and had a couple other jobs since. But Mark de Graaf has also worked on it in this paper in 2013, and we're taking his approach because it has certain advantages for the way we like to do this. Dictionary indexing is also from Mark's group. So kinematic simulation we've been doing since the beginning of EBSD, and I mentioned this equation earlier to calculate structure factors. So we find the planes with highest structure factors, and we can draw what a pattern would look like approximately, because we know the intensity's function of the structure factor. And that's great, but it doesn't really look like experimental patterns. The general location of the bands is there, width of the bands. Those approximate things are there, and that's helpful. It's gotten us this far, and we can do a lot with what we have today. But what we're doing now is dynamic pattern simulation. Instead of looking at it with structure factors, we're looking at a true simulation. So we start with a Monte Carlo simulation of 2 billion electrons within the crystal structure, and you can see the approximate distribution of these electrons as a function of energy. And so we're learning things about the energy distribution. And then we construct what's called a master pattern, and we really take into account now these electrons with the crystal structure. And the idea of this is we calculate the diffraction pattern over the sphere. So we have the entire, for all orientations, we know what the diffraction pattern looks like. We'll take that and we project it onto a square, because computers like square arrays, and we're concerned about speed, and it's hard to work with the sphere. It's called a Lambert projection. But what we can do now is we can create individual patterns from this master pattern. And you can think of this as, you can take, we know the crystal orientation, we know the EBSD detector geometry, so we can take one little piece of this sphere and project it onto our phosphor screen. And so this is what the patterns would look like. And you can see they really look a lot like experimental patterns. And this buys us some advantages for the future. We know they're not perfect. For example, look at the intensity profile across this experimental band versus this band in a simulated pattern. It's nice and symmetric here. It bounces around a lot more here. We know this has to do with absorption, and we could account for this, but it means we could not use this master pattern approach. We couldn't use this master pattern approach. We'd actually have to calculate this from first principles every single time. And that's an advantage of this master pattern is this takes hours, this takes milliseconds, microseconds. It's really quick. We can improve the kinematical simulations by including more bands in our simulation, but it still won't look exactly like an experimental one. Just to show you this isn't just for metals, this is a ceramic or a rock I've been working on, the Feldspar series, where it varies in composition, and we're trying to see how much that affects the patterns. And so now we can do that with dynamic pattern simulation, which is helping us understand why this is such a difficult mineral. So what we want to do is create a dictionary. So the idea here is we want to cover all of orientation space and calculate a individual simulated pattern for every orientation in orientation space. We save those patterns and save them onto disk. And then what we're going to do is we take our experimental pattern, and then through a dot product, we compare it against all the patterns in the dictionary. So this is thousands, tens of thousands. And we find that one of these that matches this pattern the best. So we find a best match. And you can see this is very computationally intensive, but it has its advantages. Now, one of the big challenges here is how do we sample orientation space? I said all orientations, but there's no such thing. It's a continuous space. We can only calculate patterns at discrete orientations. So the way we do that is with a cubicoric sampling approach, which I won't go into the math, partly because I don't understand it, but it's in this paper. So if you're really interested, it's here. But the idea here is we enter a target spacing between sampling points in orientation space. So let's say we want to take if we were in Euler space, we have 3 Euler angles. We would have 5 by 5 by 5 degree orientations. But Euler space is nonlinear, so this idea doesn't work. That's why we use this sampling. We could do it in any space, Rodriguez vectors, quaternions. And this just shows it in terms of Rodriguez vectors. Here's a 15 degree spacing in orientation space, 5 degrees, 2.5 degrees, and after I go smaller than that, it pretty much just goes black and I can't show it to you. So you can see it's, in orientation space, it's somewhat uniform. You can really see it here. Better than you could get with Euler angles. But it's a lot of orientations. So cubics, that 2.5 orientations was, almost 100,000 points. If I were to go to 0.5 degrees, I'm up here around 1 million. If I want to go smaller than that, 10 million. So it increases really quickly with resolution. So this is basically the resolution of our dictionary, and then this is the symmetry. You can see a triclinic material, this gets really hard. These are really big dictionaries to work with. 200 million points. So you better have a fast computer. Or the other way to do this is we're doing this with GPUs, and that's part of the way we can get to reasonable speeds. So once again, this is my nickel I did with different gains, and we're going to see how it does. There's the dictionary. It does really well. Remember, NL par was actually even a little better. But you can see this really collects data that is a big improvement, even over NPAR. So dictionary seems to work really well when we have really poor patterns. The nice thing about it is we capture the details. There's no smearing from the NPAR. It's all really nice. Just to show you, this is on my computer, which is, it's a good computer. I don't know, probably was about a $6,000 US dollar computer, so it's not super expensive, but it's a dictionary at 2 degrees, took 19 minutes to do this. And that's without the GPU, so that's pretty good, it's reasonable. It took me longer to build the dictionary than it did to do the indexing. But once you build a dictionary once, you're pretty much good as long as you're working in the same calibration. Actually, 19 of those minutes, 2 of those was just to load the dictionary into memory. But this is the quantitative indexing success rate. You see it does provide an improvement over the NPAR. I mentioned this dictionary size. The question is can we find a resolution where we have a good spacing and we get reliable indexing? So I did a little bit of experimenting with this. This is from the paper on the sampling. What we find is with the sampling, with the technique we're using to compare patterns, it's good out to about 3 degrees. After that, we can't really compare patterns. It's just, after that, they're all different. We don't know how different, but we do know they're different. With low misorientations, it actually tracks this measure, because we're not indexing, so we don't know this misorientation. We've had to calculate this different way. But what that means is, that suggests is we've got to go out to around 3 degrees to get any kind of decent results. And if we do that, this is the Huff indexing, 2.5 degree dictionary, 5 degree dictionary. Clearly now it's not good enough. We don't have enough resolution to resolve the orientation, the patterns. So we've got to go to at least 2.5 degrees is my conclusion from that. And just to show you it works for multi-phase samples, here's Huff-based and here's dictionary. It is interesting, these aren't exactly the same. The Huff seems to bias towards this blue phase in terms of deconvoluting the bands, whereas the dictionary seems to be more even in the way it treats it, which is kind of interesting. So it is interesting, we are seeing some differences at grain boundaries and phase, especially at phase boundaries with this dictionary indexing. Now, I mentioned how slow this is. Not slow, but it's just how time consuming it is. So here's what we can do is, here's our original scan. We know we've got some good data here. When we look at this, there's good data in the Huff results. So what I'm going to do is use the confidence index I try to identify the good data. So I've used the confidence index to do that, and I've indexed it with 2.5 degree dictionary. And what I find is the low CI data is the data that's changed. So the data between the Huff and the dictionary indexing, the values that have changed, the orientations that are changed, are all caught by the low CI values. So what that means is I could filter my data so that I only do dictionary indexing on the low CI points. And so here it is. Here's the data. So here's the filtering. 37% of it is relatively decent CI data, 0.1 degree, or 0.1 CI. And the data less than that is 63%. So I do 30%, 7% with the Huff, 63% with the dictionary, and I get a nice data set. And in fact, when you merge it together, it really is really good. It seems to actually be a little better than dictionary by itself. So I really like this technique, and it saves us some time, but gives us the kind of the benefits of both techniques. Just to show you, it is actually implemented in the software. We load dictionaries here. This is 5 sample patterns from the dictionary. And then we switch this to dictionary indexing and hit our button, and off it goes and does the scanning, and this finds this pattern is the best match. So this is the pattern from the dictionary. This is the experimental pattern. Like I said, these techniques are great. We can get higher efficiencies when we couple dictionary with CI filtering. We can add NPAR in a dictionary as well. Any kind of image processing you can do. It is slower, but especially as you get to lower symmetries. And once again, this is not an excuse to take shortcuts. Don't let the computer try to convince you otherwise. There are some future directions to this. Like I said, this is all pretty new, and I'm excited about these. One is pseudosymmetry problems. We may be able to use EBSD to help solve some of those problems with the dictionary. Orientation refinement, I mentioned we're doing this on, say, a 2.5 degree grid. If we think about deformed materials, we're going to have to go to much smaller grids to do that. You know, and doing a 0.5 degree grid or a 0.1 degree grid through orientation space is expensive. Computer. Not expensive, but computer intensive. So can we do some other things? And I'll show, and this is an area I've been working with, and the results look very promising. Some new efficient computation schemes are being done now. So instead of doing this pattern one-by-one comparison, you can do this in Fourier space and come in frequency space and do it much, much faster, typically a 10 times improvement in speed. So these papers are just, actually, I put these in here before they were published because I know these guys and they gave me the papers. So these haven't even appeared yet, and so this is a very new and exciting area. I wanted to mention pseudosymmetry in particular. I mentioned this pseudosymmetry problem and how difficult it is to distinguish these patterns from each other. And this example, and then this one. So I mentioned the central symmetry one, and this is the one I wanted to bring up. So, like I said, these are simulated patterns, and we can look now. We know it's the intensities that make a difference. So if you think about the Huff transform, we only care about the positions of the bands, the geometry. And so we can't see these subtleties in these, in the intensity profiles in the bands. We actually ignore the intensity. The Huff transform finds the bands it finds, and it's really good at locating, it's here in the pattern, this one's here in the pattern, but it doesn't know anything about the subtleties of intensity. And to do that, we're going to have to use the asymmetry of those subtleties. But we know we can see it with this detection, or with the dynamic pattern simulation. So we're hoping that we can use this to maybe resolve some of these issues where we know the intensity is just as important as the band position. So I haven't done any yet. I'm just showing you new things that we're working on just to give you an idea of the direction that EBSD is headed. And with that, I'm done a little early. So. Which gives us some time for questions before lunch. So.
In deformed samples, when there are huge orientation variants within the grain, so like the correction or whatever it NPAR or NPAR type of correction, so is the angular resolution only thing stopping us from doing that? Or is it
No, to be honest, we've used them for deformed materials, and I think what happens is, I was worried about the same problem because I was afraid if the patterns are so different during deformation that they would smear it out. But what we're finding is that it actually works quite well. It actually retains that orientation at the center point. And I think it's because the others kind of get smeared out and it just improves the general quality of the pattern, but the actual band positions are picked up somewhat for the pattern at the pixel of interest. And so, yeah, I would use it. Where it doesn't work well is if you have fine structures, especially twins, because then you have the same pattern on this side that you have on this side, and that's where it really falls apart.
like I work in duplex stainless steel, that's austenite and ferrite. So when I'm doing a deformation, austenite undergoes large amount of deformation compared to ferrite. So can I use a combination of this Huff and the correction to do for say austenite? Basically a correction, but ferrite would be undergoing a standard Huff transformation. Or would you please the fact?
I haven't tried that, but is it possible in the software? Yes, it would be possible in the software because what you can do is we call partitioning. So if you have a way of differentiating, it's hard though, differentiating ferrite from austenite before you index based on pattern quality or something like that, then you could index them, the two phases separately, using different image processing, different indexing, whatever you want to do.
Just one more question. So all these techniques are supposed to be done during the live acquisition?
No, they're after. They're assuming you've saved patterns during live acquisition.
So saving the patterns, does it save the entire frequency pattern itself, or it just saves the Huff space since it's a recalculated frequency pattern?
No, we save the patterns. Yeah, There's two reasons for that. One is people are asking for the most raw, they want to archive the most raw data possible. So that's the other reason. And in the end, a 60 by 60 pattern, if you work that small, that's small, 96 by 96 pattern, is pretty similar to a 180 by 96 huff. The huff's actually bigger. So you can just save the huff peaks and save the peak positions, but if you're saving the patterns too, I don't think I would save the huff peaks anymore. I think more people are saving patterns than huff peaks. You have a better chance. Let's say you set up your huff wrong, and you saved a bunch, all you saved was the huff peaks. Well, that doesn't really help you. Whereas if you save the raw data, and especially now more and more people are saving the patterns and not indexing because they're not even going to do the background correction. They're going to do the background correction afterwards too, because if you have two phases and one's got very weak signal and one's got very strong signal, you're going to want different backgrounds for those two. And so in that case, saving the raw patterns before background correction is actually a good idea. Good question though. Thank you. I think it is a little better at the grain boundaries actually. I haven't studied it yet, in detail, but just from the few pictures I've seen, I kind of get the impression we're getting a little different deconvolution of the boundaries than I think the huff is focused on really strong intensity bands, and that overrides it. So if one grain has a really strong intensity band and the other grain doesn't, I think it's biasing. Sorry? The speed? Yeah, after the cleanups? So speed and cleanup, I mean, they're somewhat not related. Yeah, sorry. My hearing's not the best. I'm getting old. You could, but you shouldn't need to. I mean, I wouldn't, if dictionary indexing hasn't solved your problem, yes, the cleanup routines will help. And I have done NPAR with dictionary, and I do get a little bit more improvement there. But I'm not sure that makes sense because the reason I would do dictionary in the first place is because of the disadvantages of NPAR. So it seems to make it worse. NLPAR maybe, but then we really got a slow thing. It'd take forever. Mark DeGraff, who's pioneered this technique with the dictionary indexing, has a really nice computer, in the big money range with like 3 GPUs on it, and he can get to speeds that are similar to the huff transform. I should say one other thing I didn't mention here. I showed a slide, but this dynamic pattern simulation is really useful for other things besides dictionary indexing. I mentioned the problem with the backgrounds. So if you've got a sample, say you have some crazy sample, it's got aluminum and tantalum in it. The signals off those are so different that the background's not going to work. So what we can do is use the simulation to actually simulate backgrounds. And we can use those simulated backgrounds, and they work just as well as regular backgrounds. And so you could simulate a background for tantalum, one for aluminum, use chemistry to differentiate the two with the EDS, and then do background correction for each one differently and get much better patterns. So I'm using it for that. The other thing we're using the patterns a lot for testing and for trying to improve our products, because the beauty of these simulation patterns are so close to the real patterns, and I know the answer. I know the orientation, I know the calibration, I know the detector geometry, I know all those things exactly. So I'm starting to be able to use the simulated patterns to really get a handle on how much uncertainty we have in things like calibration, the accuracy versus precision of orientation measurements by the huff. So we're using them a lot, and I'm hoping as we introduce this to the general community that people will start using them and give us even more ideas for answers that pattern simulation can help us with beyond dictionary indexing. the guys who do the dynamic pattern simulation are focused on that, but I think there's other uses that other people will come up with, and so I'm excited for that. I keep looking over here because he's raising his hand. So.
So I have one question. You showed that the DED patterns, you showed that the DED patterns they have much more details
Yes.
than what you will get. I was just wondering, can we use those details to get elastic strains and
That's the assumption. Yeah, we currently have a study going on with the university right now to test it.
Because if I can do that, then I can really calculate at least in 2D my,
Yeah.
because now we get an average dislocation density.
And I think for these, I mentioned the central symmetry and pseudosymmetry problems. I think those patterns can help us with that too, because I don't think we can see that kind of detail in our regular CCD, and certainly not the CMOS patterns.
And there has been some work using 3D GST to determine
Right.
the entire nice dislocation tensor.
Yes.
I believe that with DED probably we can get a much better estimate.
Right.
And use it for our simulations.
There's a couple of things we have to work out still. That kind of the cross-correlation type analysis is what we call it. The idea there is I have one pattern here, and I have a pattern here, and I want to calculate the elastic strains. And it's really a relative strain. It's really not an absolute strain. So basically what I'm looking for is if I have this feature here, I'm looking to see if this is shifted by sub-pixel amounts. And we use cross-correlation to do that. With our direct electron detection, the one thing we do have is that we have seams because we've stitched 4 together. So we're going to have to do comparisons probably within the individual quadrants. And that might be one weakness of the technique. But we can do that because now we don't have to mask out these corners because we don't have distortions out there from the lenses. So we've gained some real estate that way. We've lost some real estate because of the seams. But I'm really thinking that because of the detail, it's going to be a huge advantage. And I think it will revolutionize what we can do for strain. And like I said, I wish I'd hoped to have results before I came, but they haven't quite got here yet.
So I have one regarding the dictionary indexing. You said 2.5 degrees. So you are saying that anything up to 2.5 all will be considered all orientation?
For the dictionary versus misorientation?
Yes.
Yeah, so the way we do this is we take a pattern and we have the intensities at every point. And if you take 2 patterns, you basically turn this into one long column vector. So you unwrap it row by row and turn it into one long column vectors of intensities, normalize it to 1, and then you can do a dot product between 2 patterns. And that gives us a pattern difference metric. And it scales pretty well with misorientation down to about 3 degrees. After that, there's no correlation. 50 degrees is the same as 10 degrees. And so we can't use that pattern difference metric beyond probably about 3 degrees. And so that's why I showed that graph. Now, we have talked about, are there ways to interpolate using that between patterns to try to get an idea of can we refine that way? And the conclusion has been it doesn't really work. Not totally sure why. I still think it's worth trying again, but the orientation refinement is basically you simulate, you're going back to simulating patterns. Instead of trying to create a dictionary, use the dictionary to find a starting orientation and then actually simulate, a certain degrees away, see how much it changes, use the optimization routine to hone in on the right answer. And Mark's done that. He thinks the best you can do is probably about 0.1 degrees. I think you can do better. I really do. I think he focuses on smaller patterns, say 60 by 60, which is great for doing the comparison, the dictionary, but I think when you're actually doing this refinement, you need to go to bigger patterns, say 120 by 120 or larger, to really get the orientation precisely. And all this, it's all doable, depending on how much time you have, because it does take time on the computer to do this, and bigger, more expensive computers.
So you already implemented this in the 8.1?
8.5. Yep. So it's an add-on module to 8.5. 8.5 has a few other features. One of the big ones is we're introducing new data collection software called Apex, which you should be, I assume, will be getting for your new camera. And it has some new file formats and some new things. And so we have to put out a new release anyway to support that. But so we've added this add-in module as well. And it has some new reporting features that will be really helpful.
So any simulation tools in your software, because now that is helpful?
Sorry?
Do you have any simulation software, modules in your software so that you can pattern simulations, dynamical applications?
Yes. So yeah, it's implemented in our software, dynamic pattern simulation. Like I said, it's an add-on module. You have to pay extra for it. But.
I just remembered one more question. You mentioned in the earlier talk that EBSD can be used for face identification.
Right.
What my probably assumption was that we first used to do X-ray, get the phases which are present, and then include those phases and try to index. So how can we do kind of identify the phases if I have a pattern?
Yeah, and it comes down to what do we mean by the word identification. So that's usually what we think of in phase identification. You have X-ray results or you have EDS results, so you know the chemistry. You go to a database, try to match a phase in the database. So it's really a phase matching process, template matching, if you will. It's not true phase ID. There has been some work done on trying to, we did some early papers and there's been some good work out of China and some other places where they're really trying to back calculate. So start out, try to maybe figure out what the unit cell is from the patterns themselves, knowing nothing about the crystal ahead of time. It's really hard. And part of the reason it's hard is because we can't measure bandwidths well. And that's where that direct electron detector is going to make a difference, because now we can measure those bandwidths quite precisely. And so that tells us, if you know the bandwidth, you know the D-spacing. And so now you can start to understand maybe more about your crystal structure without that a priori information. So yes, I do think it's an area. That's the problem. I get excited, I introduce a new camera, it just creates more work for me because now there's more ideas I have to chase. Oh, there's a question way in the back.
So this might be related to the monitoring.
Just 1 minute.
They want to record you on the camera, so you can be famous.
It might be a basic question, but when you, for example, you show the EBSD map of a road sample, you said it's an ND inverse pole figure. So generally for road samples, we show the ND IPM.
Right.
For example, if you want to look at the basal texture in titanium, it's actually the TB IPM. Means you look at the TB.
Right. Yeah.
So is there a standard way of representing your textures? For example, even in my steel, if I'm going to measure the RD ND section, I rotate 90 degrees about A1 to bring it to ND IPM.
Yeah.
So is it a standard way that you always present ND IPA, or is there something like it's just that
No, there's really not a standard way, and that's because, like you said, there are standards out there because there's examples in the literature. But there may be other ways to represent the data than what's already been done, say, with X-ray results. I think you bring up a really good point. Can you see this at all? This is really tough. I know it's green on green. It's a little tough to see, but I think a good example is I showed that we had a substrate and then stuff growing on top of the substrate, right? So we cut the sample, so we looked at this section. Well, an ND inverse pole figure is going to show you, this is the critical direction. But the reality is we probably want to look at this direction. And so yes, it makes sense to rotate the data or rotate the pole figures, which we're working on, so that you can look at it in the direction that makes the most sense for the physical aspect of the material you're trying to understand. And so I think it's the processing that governs what is a standard way to look at it. And so I think it's, I think a great example is additive manufacturing. you have temperature gradients you think you might know, and so you could use that as a standard, a reference frame. But I've seen samples where the gradients are going every which way because they're changing them, and now I don't know the best way to represent that data. It's hard for me, and those textures are new to the community. So you have an opportunity or a drawback of not knowing what the standard is, and so there you have to go with what you know. Good question. There's another one behind you there. Okay.
So one of them is like we told that there's technique like iron milling or which can be used for the sample preparation of magnesium or a magnesium alloys or titanium alloys and so forth. But I have a question that such iron milling techniques reduces a lot of heat in the sample.
Right.
So when we are dealing with techniques like EBS, this gives us a very surface information of the whole sample.
Right.
Then definitely we are losing some information relating to the distribution density and all other stuff.
Yep.
So is there any alternative to that, like for instance, or something which may prove a better technique for watching samples or sample preparation?
Yeah, like I said, we've used colloidal silica for that. It's a real problem on all materials. My colleague David Field did some interesting work where he did synchrotron. And it didn't match up with EBSD as well as we had hoped. And so I think we are introducing some deformation in the surface of our materials, and that's just part of what we're, when we do sample preparation, that's part of what we do. And we can't assume it's always the picture of the bulk that we'd like to assume. And I wish I could sit here and say EBSD gives the true picture every time. But I think one of the things we've learned from EBSD over the past 20 years, because it is such a surface-sensitive technique, is that really sample prep's more important than we've ever thought. Because I think we've looked at optical microstructures, we've looked at SEM figures, and we've probably assumed that was the bulk, when in reality, if we weren't careful in our sample prep, it's an approximation of what's in the bulk. And I think that is just an uncertainty we kind of have to live with. The synchrotron is great because it's through thickness work. You can do some amazing stuff. And if you have the ability to do that, I would, sure, go for it. And then compare it against your EBSD results to make sure that we really understand our interpretation of our materials and their behavior and their microstructures. I think that's just a general kind of thought in metallurgy that maybe EBSD has helped highlight and helped me to understand better. So I wish I had a good answer to say, yeah, do this, this, and this, and you've captured the true microstructure, but I don't think we ever really know that. And so looking at different cross-sections, looking at, different, and that's why we still need X-ray and we still need these other results, because it gives us another check. It may not be a one-to-one comparison, but at least it's a check on what is really happening in our material.
Another question is the fundamental costing of especially magnesium, because magnesium is generating quite noisy pattern.
Yes.
Fresh sample preparation, we may get, we have a nice probability to get a noisy pattern. Now when we do some crossing like holding or some kind of operations like that, because of the distortions, we get kind of diffused, even in the noisy pattern, we get diffused diffusion patterns and all that. So now when we complete this to post-emergent pigments and all, we get decrystallization where we get kind of clear patterns in some areas, diffused patterns in some areas, because of the partial decrystallization.
Partial, yeah.
So now we have some regular introduced to some post-processing techniques like NFR and NFR and so on.
Right.
So NFR, they may work well in the places where there are diffused patterns, because there we can get a clear microstructure, clear understanding.
Right.
But in cases where there is complete decrystallization, some grades may be completely decrystallized. So there we do not use NFR and NFR. We can use a half patterns.
Right.
So does this new approach taking the approach making the microstructure techniques? There is some places where there is no decrystallization and some places there is.
Yeah, I think the dictionary indexing may help with those kind of problems. Like you said, that when image processing is not possible, oh well. The one picture I had with was magnesium, the deformed magnesium. And you could see, we started out at 54%. The best we could do was about 64% indexing. It's still not great. I still worry that it might be biased, that we can get some orientations and not other orientations because of the way the dislocations are being stored in the material. That's always my worry when I see poor indexing rates, is that there's a bias towards one orientation over the other. And I mean, X-ray will resolve the question of if there is a bias, but it can't help me solve a pattern indexing problem. So I wish I had a nice magic wand to solve this problem, but you're running into the same problems we see, and we don't have perfect answers for it. We just do the best we can and try to make the interpretations from what we know, and like I said, use other techniques to confirm that and make sure we aren't misleading ourselves. So. I'm sorry you have to work with such a difficult material, even though it's an important material right now. So I hope, make sure you scour the literature and talk to other people, but you're not the only one seeing those problems, and other people are seeing the same problems. And magnesium has probably been the material that we get the most questions about. And we have to say, I'm sorry.
Not high entropy alloys?
Yeah. That's next, probably. When people get bored of magnesium, they'll go switch to that. But those are all good questions and valid concerns, and like I said, I wish I had good answers.
So I have one final question regarding the IPF regime.
Yes.
So is it the best way, or is there better ways of color coding? Because I have seen some papers recent times where they say there are better ways of.
Yes.
So
they have been implemented in 8.5.
Okay.
I don't know. Am I talking about that tomorrow?
Okay, then really let us wait for people.
No, but I'll add some slides in the hotel tonight for tomorrow. Yes, it is an area we've added. There's been, you're right, a couple of papers show it's not a big concern for high symmetry materials, but for low symmetry materials, it's more of an issue. Yeah, there are better ways of coloring. I didn't want to do it because they involve, so the colors we use, red, green, and blue, to do our color mixing. But the new ones involve adding white and black, which is fine if you're just doing a color map. But if you want to overlay it on an IQ map, that gets confusing as to what's color and what's grayscale, And so I avoided it. And plus, I didn't want to write the code, but I have since done that in this 8.5 release. So, timely question.
So, do you have any more questions? Or we will break for lunch? Okay, then we will break for lunch.
All right.
So the plan is the lunch. Everybody got a token. Yeah, and you can go to the staff canteen there. IIT students can guide the IIT Madras students can guide the other students. So after that, we again move to IC and SR, all three. So again, IIT Madras students can guide all of you. So the live demonstration will be streamed over there. So by 2 o'clock, you can assemble there. And no, yeah, you can carry your stuff.
Okay.
It's generally safe, but I can't assure. Any other announcements? Okay, by the time so lunch will be ready by 1:15, so you can slowly go.